subcommittee on risk applications. So I am more on the risk-informed side of risk-informed performance-based, and Prasad is definitely more on the performance-based side. Names on the task group, you'll be hearing from Brian McDonald and Andrew Whittaker after our presentation. Heard from Ronnie earlier today. Doug Clark will be joining us online, and Prasad hopefully is joining us in the room shortly. Next slide. So our task group was created largely because in the Advanced Reactor Roadmap, there are 2 action items now under risk-informed performance-based codes and standards. One is a pilot of using risk-informed performance-based concepts to inform update of a standard. Then there is a new one this year, which is what I see more as a maintenance and upkeep, right? Continue to track how standards are moving in a more risk-informed performance-based manner, get the feedback from the developers to inform and continue pushing codes and standards in a risk-informed performance-based direction. The task group's been meeting biweekly since May of this year. We've got a good start on a guidance document. We are trying to get at some of the items that Prasad was mentioning this morning. There should be a shared understanding of what risk-informed means, what performance-based means, what risk-informed performance-based means, how to use those concepts when engaging with the regulator, how they have been used, right? Like, risk-informed and performance-based isn't new. I'd argue it's been going on well before, even 98. There are a lot of good regulations out there that are risk-informed performance-based. There's standards that are risk-informed performance-based, but it's a continuous process, right? So does make it a little tricky to close an ARCSC action. I would argue that there have been lots of pilots already of risk-informed performance-based standards. Prasad, come on up.
You don't have to sit down.
Yeah. But
Try to hang on.
But yeah, our risk-informed performance-based guidance document, for those who are members of ARCSC, you can go on the SharePoint, you can see the draft version of it now. There's a lot of good information in there, and we're working to get that document finalized and published, hopefully early next year. And the idea is for it to be used, right? If you as a developer, if you as a regulator, if you as a volunteer for a standards development organization have a desire to make your process, your standard, your regulation, your whatever, more risk-informed and performance-based, we're trying to build a tool to help with that and provide resources. Like, we are a team that is available. Send us an email, ask us questions, because all of us are volunteering our time to help make codes and standards more risk-informed and performance-based. And Prasad, you wrote the slide.
Okay, thank you, John. Now, if you don't mind, I'm going to sit down. I've got leg problems, so. Oh, okay. Yeah, maybe I'll just sit here and, yeah, I guess I can see the slides here. Yeah, thank you, John, for getting us started. So one of the things I mentioned earlier was that this guidance document is not going to be a traditional document as such. It's going to be a living document in the sense that it is a framework for decision making. In fact, I want to stress that in order to be risk-informed and performance-based, I think it is important not to seek to document all the requirements, and that is why the way we are structuring this is guidance for designers as well as for standards developing organizations. Because when I think about, what is common between the work that designers do and what standards developing organizations do, it is to develop requirements. And, it is in that respect that it is important to recognize the commonality. So this document is meant to be used by designers. And, next slide. So as I see it, the central effort of a designer who is given responsibility for a project is to accomplish the project cost effectively. So, in order to accomplish the project cost effectively, as I see it, and I think what we are going to try to point out in this guidance is that all the requirements associated with the project have to have some kind of relationship. There has to be a definition of the relationships and the dependencies among the requirements. And in order for that to happen, we can look at the overall project objectives. And this could be something like the entire site of of a plant. What I have in mind is a site that, let's say, used to have a coal-fired plant, has the energy conversion features already in there, and what is required is to replace that coal-fired plant with a nuclear source, nuclear power source. So the reactor is just a heat source. You don't even necessarily have to know what is that reactor. But the requirements management comes in when you relate the requirements associated with this reactor, whatever the technology, when you relate those requirements all the way back to the project objectives, and you're able to show that there is a reason for every requirement over there. So in terms of the regulatory requirements, it could be a small subset, and it should not be what determines the viability of the whole project itself. That's what I think of as a truly performance-based implementation of nuclear technology. Next slide. Now, the existing practices in some ways are not optimal to realize these kinds of objectives. And what I think we have found in recent years is that you need practices that are associated more generally with systems engineering, and the kinds of requirements management that is described. I would say where I have found a very good description is in the NASA Systems Engineering Handbook, and I see this approach as being cost effective because without having this kind of traceability of requirements, what tends to happen is you create silos, and there is almost always friction created when you have silos in the process. So, you know, a key part of the systems engineering approach is to have a continuum of requirements between design, construction, operation, and decommissioning. And this is where, you know, current practices are you know, not consistent with what I think of as efficiency. So, you know, what happens when standards developing organizations get into it is that they see where the current practices are, and they will, you know, look at the need for a standard in terms of the way the current practices work. And, you know, in terms of what has changed by way of modernization, I think what the commission issued back in 1999 in this SRM to SECI 98-144 created a whole different paradigm. One of the key aspects of this white paper, Rani described it, you know, in her presentation, and she gave the attributes, the definition of the performance-based approach there, is to encourage and reward improved outcomes. In other words, you know, too often in current practice, a product or an output of an activity is equated with the outcome. I think one of the key differences of using an RIPB approach is to be outcome focused, as Rani described it. And, you know, in order to be focused on the outcome, you have to look at all the different products, see how they relate to one another, and see how they contribute towards the overall project objectives, you know. And I believe that the, you know, the recent legislation, NEMA, the Advance Act, and the executive orders all call for an approach that is efficient in this manner. Next slide. So this is where this idea of requirements management and the way it is defined in the NASA handbook comes in very handy. Requirements management is the process of documenting, analyzing, tracking, and verifying requirements throughout the system development lifecycle. The purpose of an objectives-driven structure for a reactor product, that is just now, the reactor product is just one part of the overall project. And, you know, the objectives of the reactor product would be based on a set of requirements in which all the acceptance criteria on the objectives would contribute to the overall, you know, the mission statement as shown on the right. That's the pyramid that Rani used in her presentation. And what you see on the left over here is a graphic, is a picture from the standard ANS 30.3, which also calls for a sort of a structure in which you begin with the plant level safety functions, and then you decompose those safety functions into greater and greater levels of detail until you get down into the component levels. So the broad base of this pyramid is really consisting of the whole range of requirements that may include things like procurement requirements, but the fact is that if it is done in an organized way, then every requirement that is associated with the procurement of a product, of a component, would have a traceable and trackable connection all the way up to the success of the project itself. Sir?
I did want to add one thing on this.
Yeah, sure.
One other very important benefit of doing this and doing it rigorously, especially for the next 2 years, regulations, that top level requirement is going to change a lot, right? The wholesale rulemaking revision has started. For those who read the Federal Register yesterday, 10 CFR 5150 for aircraft impact is being sunset. Come January 2027, that is no longer a regulation. That's no longer a requirement. And any design requirements, design decisions that you made to account for that, if you have a good traceability matrix, you can identify, hey, these design requirements are no longer needed. Now, I still need to design for earthquake, tornado missile, all these other hazards, all these other regulations, but if 5150 goes away as proposed in the FRN yesterday, like that is no longer a design requirement. So this sort of process can help with a lot of that, which might be coming in the next year or so as the wholesale rulemaking moves forward.
Thank you, John. That was very helpful to make the connection with what's going on today. Next slide. So the point that I'm making over here is just very simple, that there is a symbiotic relationship between what designers do and what standards developers do. Because the designers say, I need a standard that does XYZ, as Rani described what deep fission needs. Now, we can have standards that have a lot of detail in it, but, if they're not necessary to meet the designer's needs, then it should be possible to just say, well, it's nice that the standard exists, but I don't need it. I'm going to find a voluntary consensus standard that has been certified by an accrediting organization. And what we use in this country is ANSI, the American National Standards Institute. And, they have all the process requirements to create what are called American National Standards. And so if it is an American National Standard, then, it's more important to focus on the project success and avoid, all the frictions, and I believe, save a lot of money along those lines. And, I also wanted to point out how the requirements themselves can be more easily harmonized among different standards if you can trace the requirements to the higher level objectives, which generally are common. For example, in the Part 53 rulemaking, the highest level performance objective, at least in the proposed rule as it was issued a couple of years ago, was retention of radioactive materials. So as long as you're able to show that there is retention of radioactive materials assured by the design, the design process and the design features, it should be okay to find commonality among the requirements, different ways of doing it among the different standards. So all this is possible if we use a methodology that is described in the NRC's guidance document for performance-based approaches, NUREC BR 0303, which Rani referred to. And this methodology provides for this kind of traceability and the tracking of requirements. So next slide.
And one thing I want to add is just, so how do you use this as someone working on a standard within an SDO, right? These standards were developed over many years and very good, but with some assumptions around what the high level mission was, right? ASCE 43 for a very long time rightly assumed the building is containment. It cannot leak. That is no longer a necessary assumption. So any design requirements in that standard that flew down from the building cannot leak are not required for some of these designs. Similar with IEEE, like single failure criterion was so baked into the regulations, it is assumed to never go away. LMP says that as long as you can ensure reliability, it obviates the need for strict compliance with the single failure criterion. So any parts of those standards that are laser focused on that criterion could allow for more flexibility, more performance-based. And I think that sort of thing can inform any standard out there, going back to the purpose and making sure that the standard allows flexibility for these different purposes that you want it to be used for. And Andrew, I saw you.
Yeah, we're going to try this a third time. Third time's a charm. Looks like Ralph Hill has his hand up. And I believe it has to do with the current discussion. So I wanted to see if we could hear you, Ralph. Go ahead and come off mute and ask your question.
Yes, Andrew, can you hear me?
Woohoo! Yes, we can. Great job.
Thank you.
Thank you.
Good. So in response to your question, the requirements, whether they're originating requirements, as Prasad's talking about top level requirements or requirements that are derived for the design from those, they're allocated to the systems, well, the facilities, their systems, the components that make up those systems. They're allocated down to those. And we, in the plant systems design and systems engineering in general, we recommend using a requirements management software or tool that allows you to maintain traceability to those. So if you get a change in a requirement, not only can you capture that change in the tool, but it also points to all the places that that requirement has been allocated to. So that's a key portion of your requirements management process. I hope that answers your question.
Thank you, Ralph. So I'm trying to relate all this to something key to the structure that I've tried to talk about, the objectives hierarchy, which is basically a structure of performance objectives. So I think there's a way to look at a performance objective in terms of, what is the anatomy of it? A requirement is just something that you put as an acceptance criteria on the parameters associated with a performance objective. So if I'm beginning with the requirement now and saying that, let's say the high level requirement is just a deployment of a reactor heat source in place of a coal-powered heat source. That would be the high level requirement. At the lower levels, where you have a high degree of level of detail specified, it should be possible to just look for procurement of off-the-shelf items, for your components, and see to what extent they will be able to fulfill the functional aspects of the of what is needed to make this reactor work. Reactor and also all the the heat conversion system. So the criterion is just setting this level that assures that you meet your objectives, and the objective itself is just a set of activities that is directed at accomplishing a purpose. So what this was part of a presentation that I made for the community of practice for ANS, and the idea is that the attributes of the Commission's definition of a performance-based approach can be directly related to these kinds of ideas here. Next slide. So I mean, in terms of what we are doing in the task group, the RIPB task group, this guidance document, because it already has referenced a wide range of existing documents, we have identified a lot of the documents. In fact, right now, I would say, something like 80% of all the documents needed, are already identified. We haven't necessarily, provided all the details on each of these documents and how they meet the attributes. But in general, the kind of document that we refer to is a guidance document that is currently being used in ANS, RP3C. And this guidance document describes what are the attributes of the risk-informed approach and the performance-based approach. And the risk-informed attributes are related to reliabilities, whereas the performance-based attributes reflect margins, and the margins are expressed as differences between system states. So this is where, a system can have, under normal operating conditions, it would be in the acceptable range, but there would be some set of conditions at which the parameters associated with this operational state would become unacceptable, either because of changes in the physical environment or other scenarios imposed, such parameters reflect the acceptance criteria. And so this kind of decision-making framework for requirements management will offer more choices to designers and the SDOs to enable innovation, and it will also support incentives for improved outcomes, because when you are working with margins, you may have much more margin than you need, in which case the way to save costs may be, find an alternative that fulfills the functional need, but does so with less margin and lower cost. So I believe this whole thing will contribute more towards economizing the nuclear option. Next slide. I think that's the last one. Yeah. Oh, yeah. All right. This is the contact information. My name there, John, and because I've referred to a lot of the community of practice sessions, that's available on that site, and of course, Scorer. Maybe John can talk about the Scorer.
Yeah, this slide is mainly just to highlight, if you are working on a standard, if you are working on a design and you want to do more to make your design more risk-informed and performance-based, there are resources out there. Our task group, you can reach out to me or Prasad, and our task group is happy to work with you. ANS has their committee, ASME, ANS, the joint committee has SCORA. There are a lot of resources and a lot of knowledge on how to do this, and we want to help. The other piece, RIPB is a bit of a buzzword. If you are frustrated as a developer with anything too prescriptive in your code, talk to us, right? Bring it up at the SDO, the committee meetings themselves. But if you're struggling on how to change what's in the code from something that is prescriptive to something that is more performance-based or risk-informed, these are the groups you can reach out to try and make that happen. And then for the rest of this presentation, we want to share the people who are doing that work. So ASME has made some great progress. I'm personally involved with ASME Section 11, Division 2, Reliability Integrity Management, which goes up good long way into moving into the more performance-based direction. And Rachel Romano is going to be talking to the work she's been doing through the Section 3 Division 5 committee. And then we'll have Doug Clark. I want to verify that you're online. We'll go into your presentation following Rachel.
Yes, John, I'm online if you can hear me.
Thanks, John. I'll wait for my presentation to get up there, but in the meantime, for those of you who don't know me, my name is Rachel Romano. I'm with NPR Associates, and I am here representing Section 3 as the secretary of the task group on alternate requirements. I made sure my phone of friends are online, so Dale Matthews, the chair of Section 3, is also online and can help if there's anything that I miss, but very pleased to be here, and thanks to John for letting me chat about what Section 3 is doing to be a part of bringing risk-informed thinking into codes and standards development. So next slide, please. I'll just be presenting for the next 10 to 15 minutes on the work that the committees are doing to ensure that Section 3 meets the needs of the advanced reactor community. So you can see we'll just talk about some of the activities that Section 3 is doing, how Section 3 is increasing value, and then some specific activities of note to this topic of risk-informed, performance-based work. So next slide, please. So first, I just kind of wanted to give an overview and kind of say that Section 3 is committed to making sure that the code does not lag industry needs. I know that's a common thinking when you think of ASME Section 3 and standards organizations are that they're slow. And so I know the Section 3 leadership has been working really hard to make sure that we have the right input from stakeholders to steer the direction of the committee work. And so that takes place via many different forums of the actual advanced reactor designers sending representatives to the code meetings. But there are also annual ESAC or Executive Strategic Advisory Council meetings, which provide a forum for Section 3 leadership to hear directly from executives on these advanced reactor developers on their most pressing needs. And then, of course, there's the ARCSC survey from this group that provided valuable input as well. And so the recent activities that are shown here all evolved out of those inputs. And I know the other important thing to making sure that Section 3 is supporting the needs of the industry is speed of publishing new code requirements that evolve. And so new code editions are published every 2 years. There's also the vehicle of code cases, which are another opportunity to get rules out to users more expeditiously as needs arise from users. And so as part of my work, we've worked very closely with groups like NEI to get NRC engagement via public meetings as well on key concerns for stakeholders to smooth the path for regulatory acceptance. Next, please. And so I just, of the current activities that we have shown here, I'm going to highlight the two shown below, one of which I've been very intimately involved with for the last 5 years, and the other, which is relatively new, but a very exciting opportunity that I'm also a part of. Next slide, please. So one of Section 3's strategic initiatives is increasing value. And so that broadly encompasses Section 3's desire to address the unique safety case of advanced reactors. So you heard from Ronnie earlier, there are folks that are pursuing many different kinds of designs, all of which have very unique features that make them different from the traditional PWRs that inform the development of the ASME Section 3 codes. And part of that includes components that are part of the nuclear pressure boundary that maybe don't have the same safety case or risk significance as in a light water reactor. So there's still the need for the design rules that we have in Section 3, but not a need for some of the additional requirements that have been baked into the code. Again, going back to John's points of what's the high level rationale for why these existed in the first place. So when I say alternate requirements, we're working in this risk-informed safety categorization framework, which evolved out of the recognition that there is a need for graded approach. So while Section 3 is a component code and we do not have any part in how the categorization takes place, we wanted to provide a set of rules that could be used if the owner, in conjunction with the regulator, have agreed that they have a component that falls into this intermediate safety category. So we're looking to remove or replace requirements that are not appropriate for items in this category, which provides a construction option that maintains the nuclear design rules and margins, but does result in reduced costs and schedule that are more appropriate for this scope of components. And so again, I want to highlight that similar to the kind of the risk-informed performance-based thinking discussed previously, we're trying to take the approach of defining minimum requirements and using the technical basis of the safety categorization to support that, providing that in the Section 3 standard. Next slide, please. So I know many people are thinking, why Section 3? There's a lot of codes and standards out there. And I do want to take a point to say, I am not saying that Section 3 is the appropriate option for everyone based on your safety case. I want to make the point that there are very many unique needs, and we saw a need based on our discussions with stakeholders to provide an option within the framework of Section 3 if it is advantageous. And some of those reasons might be that there is a single code of construction, and that is very beneficial to streamlining the process for getting certification. It appropriately accounts for the unique requirements of nuclear applications. So I can speak more to the technical details some other time, but that includes some of the creep design life and other seismic rules that you have access to in nuclear codes that you don't have in commercial codes at the moment. And I will say as an aside that Section 3 is actually working with Section 8 to talk through some of those design rule gaps and maybe help address those. So there is some collaboration going on there. And then I know this was a topic of interest earlier as well, but at least at this point in time, when there is some concern about regulatory acceptance, as the industry moves towards this different way of thinking, that the use of the consensus standard is very helpful to reducing uncertainty and improving regulatory acceptance of these designs. Next slide, please. So at section 3, we played our find the money game and looked for ways where industrial code requirements offered improved value compared to the nuclear construction requirements. And so the key areas that we found were material procurement, NDE and testing, and quality assurance. And so we came up with a long-term strategy that we started way back in early 2021 and have continued to date to get options out there to users to take advantage of each of these. So rather than trying to tackle this in a all big one and done case, which we started trying to do, we have tackled it in bits and pieces, and that has helped us to gain acceptance along the way and hopefully pave the way towards more larger scale strategic changes, which I'll talk through with the task group on Div 6 shortly. So next slide, please. So first rule that exists out there is alternate requirements for material procurement. And so all these alternate requirements are for components within this scope, which we call commensurate with their contribution to safety or risk, which is our fancy way of trying to be categorization process agnostic to just the components that fall in the intermediate safety category, where special treatments are required, but full high safety and full stamping to section 3 may not be required. And that's been recognized through the regulatory framework. So this permits within the scope of section 3 for this scope of components, procurement from a supplier other than a material organization. So that's helping address some of the supply chain issues that we've heard. The next one is our alternate code case for non-destructive examination and testing. So that's code case N940. We're currently working on getting revision 2 published. I think that's at the Standards Committee again. And so this really provides us 4 key opportunities to reduce costs and schedule, commensurate with the item's contribution to safety or risk based on our engagements with stakeholders. Next slide, or next bullet, please. And the part of this that we saw as being one of the highest value, but also the most challenging to tackle was alternate general requirements and specifically alternate quality assurance programs. So we actually have an open record out now for ballot at some of the subgroups and for comment at conformity assessment. And what we are looking at there is for folks that already have a Section 3 certificate, how can we help provide them alternate minimum quality requirements that would let them take advantage of some of the processes and procedures that they use maybe in for producing commercial products that could allow them to see costs and schedule savings. So this has been great for providing rules to users within the current framework of Section 3. And I'll just show one more slide of, wow, these rules are amazing, Rachel. How you want to use them, that's amazing, but how do you do that? So next slide. For those of you who aren't as familiar with the code process, this is a figure I pulled from our technical basis PPP paper, which talks you through where the responsibility lies for performing categorization, which is again outside the scope of Section 3, but determining which code you want to use, determining the code classification, and then you as the owner or their designee, which might be a Reactor designer, would be responsible for selecting the appropriate codes and standards for construction and specifying code cases such as this one in their design specification. And so if that is determined to be appropriate for the selected categorization process, then the certificate holder would implement the alternate requirements at the direction of the owner or their designee via that design spec. So that's just a brief bit of implementation on the requirements. Next slide. So the other activity that I want to highlight is investigating the creation of Division 6. Now, this is not actually the goal. This was selected, the name of this task group was selected as a way to intentionally engage differently and at a higher and more comprehensive level than what we were doing at the task group on alternate requirements. And that's really because through the work that we've been doing, we being the task group on alternate requirements, we identified a number of themes and challenges to implementation within the current framework in ways that perhaps the utility of the rules that we're working through may be limited based on some of the things we're hearing from stakeholders. And so one of the things is supply chain is a key issue for cost and schedule of construction. And if you look at, if you say need to stamp to Section 3, there is no way to simply apply or accept another standards rules and still stamp to Section 3. But we do only have a limited scope of, or supply of Section 3 certificate holders compared to the demands of the industry. So we really, if you click the next bullet, really needed to determine an overall strategy to construction and stamping that is defined and permitted by the code if we want to continue making this user-friendly and a good option for folks to consider. So next slide. This task group was only created earlier this year, so it's very much fledgling, but had really great discussions so far, especially at the last in-person meeting. And so the task group is exploring a number of options and working on a white paper planned to be published in August of 2026 that presents the general framework based on these conversations. But some of the questions that we've been discussing include some of the things that I think I've heard earlier today. You know, one path is maybe permitting a certificate holder to only have alternate requirements items in their scope of certificate, thereby reducing the barrier to entry. Maybe a way to permit fabrication activities by contract without the need for a full NPT certification. We're discussing questions on how or should lower risk significant items be distinguished if they're still within the scope of Section 3. And then with the graded QA, you know, we've had a lot of discussions with our friends in NQA and the NRC that remind us that graded QA is not new, and it's in fact written into Appendix B and NQA 1, but it does need to be incorporated within the context of subsection NCA for it to be useful for users here. So next slide. Just to wrap this up, I hope this discussion highlights that the Section 3 committee actions are driven by input and needs from stakeholders that show up and participate, and the overall focus areas that we have are driven by strategic objectives from the leadership team. And our work on alternate requirements for items commensurate with their contribution to safety or risk is benefited by the consensus process and expert reviews from the code committee members, which I think is a very high value add of using a consensus standard like Section 3. And so I hope everyone, if you click one last time, will walk away from this presentation with the understanding that Section 3 is reestablishing construction rules that evolve nearly real time with industry and stakeholder needs. So last slide is just for discussion, but thank you everyone for listening and your time.
Rachel, one of the things that I'm trying to understand better is how ASME and ANS define the term components as part of what we call SSCs. You know, for example, in your presentation, you described ASME standards as applicable to manufacture of components, right? In ANS, the basic unit that we use is, we call it SSC, taken directly from Part 50, you know, and 50.2 talks about system structures and components. And I'm trying to see how, you know, within ASME and the rules that are provided for the construction of components, how that relates to SSCs, you know, is there a definition within the ASME framework for how components are relate to SSCs?
So the question is there a discussion on how ANS defines structure, systems, and components, and ASME is a component construction code, and is there any definition within ASME on how this component definition relates to the ANS definition? And I will, to that, Section 3 is a component construction code, and so it is very limited in scope of what it can and can't provide requirements and rules for. So there is a definition for components in NCA 9000. And in fact, in the requirements that we've provided here, we are very specific to say items commensurate with their contribution or safety risk, because I understand that the term component has a very distinct definition in Section 3 construction. But in terms of relation to other standards, I don't think that ASME has any plans to define, to link in that way to standards like ANS.
Yeah, and Ralph Hill actually dropped in the definition, and as you had mentioned, component, a vessel, concrete containment, pump, pressure relief valve, line valve, storage tank, piping system, or core support structure that is designed, constructed, and stamped in accordance with the rules of this section.
Thank you.
So it should be possible to use the term SSC without, like the next presentation is going to be on ANS 226. And there the discussion will be on SSCs, and seismic categorization of that. So, maybe there is no relationship between the way ANS uses SSC and the way ASME refers to components.
Yeah, it's very specific to the stamping requirements and is defined in explicit code terms, as Ralph mentioned. But yeah, thank you for the question. Are there any other questions? I appreciate the time.
I don't know if I need to transition, but Doug Clark, you're up next.
Yeah, before we do that, there was one comment or question in here that I think I missed the context for, but I think it occurred when Prasad and John, you were speaking. This is from Allison Coates online. Please clarify that 80% of documents have been identified. And it looks like you know the context.
Yeah, I think I know the context. The comment Prasad made, we're in our risk-informed performance-based guidance document that we're pulling together. We wanted to reference and have a short discussion of what we saw as the really key examples of risk-informed performance-based, whether it's NRC guidance documents, SECIs, new regs, standards that are risk-informed performance-based, regulations that are risk-informed performance-based. It's obviously not a very specific number, but we think we have a good cross-section captured of all the available risk-informed performance-based guidance out there. Anything you want to add, Prasad?
No, I think you captured it. It's basically we don't need to wait for anything. We have enough in hand to proceed.
All right. Anything else? Then over to you, Doug.
All right, John, you can hear me?
Yep.
All right. So greetings, everybody. My name is Doug Clark. I'm the chief engineer at the Y12 complex here in Oak Ridge. I support everything going on in the Oak Ridge Reservation area, and I've been the chair of the working group for 226 since Quasi Hussein stepped down in about 2017. And what we want to do real quick is walk you through 226 and show that it's been risk informed and performance based since 2004, even though some folks sort of run over it real quick trying to get their structural engineers the input they need. The standard provides a good framework. So next slide, please. 226 doesn't stand on its own. It interfaces with a lot of the other ANS standards, and it has allowed for certain levels to use the building code. Right now, it's a mix between ASCE 7 and ASCE 4. It relies heavily on ASCE SEI 43 as the seismic analysis goes. So the standard is a crux that lets a lot of different inputs flow through to determine the design categorization and the limit states. For those that are wishing to use this standard, DOE uses this for more than just seismic. DOE uses this for all natural phenomena, so they use it for wind, precipitation, volcano loading. The standard is specific to seismic, but the concept of how you interface with all of your different site hazards curves works for multiple different standards. If you'll go to the next slide, please. The standard has always had a mix of qualitative criteria and quantitative criteria, which then step up based off of the consequences to the workers, the public, and the environment. As we get the move on the right, the quantitative table, which has been in Appendix A, is in lockstep with DOE and a lot of the regulation points in the enabling legislation. So 25 REM to the public will generally get you into that SDC 3, Seismic Design Category 3 limit. But you still have the option in the 2004 version of using these qualitative thresholds. There has been a move to more quantitative just for consistency basis, but they're in there, and it's a graded approach or risk-informed approach based off of consequences. Next slide, please. The main thing that everyone comes to 226 for is this limit state, and I'm going to address limit states A, B, C, and D. Basically, it's going to say what is the damage. Some of the terms have been used differently. The terms on this slide are straight out of the standard. DOE basically states that limit state D is going to function before, during, and after an accident, and they grade the approach through otherwise. There are appendices in the standard that basically go through the component level. What are you looking at? This helps the designer up front and the analysts look at the component they're at in their system while they're designing it and feed back into the designers what needed limit state they have. That's going to be for any objective in the objectives hierarchy. What generally happens in application here is the final limit state that is fed back for the seismic design demand is the highest limit state that they identified for any upset. But here's the examples. There's some for structure. There's some for the buildings. It's quite a long appendix if you wish to go look at that. But once you've assigned the limit state based off of your component, now you move into a structured approach. So next slide, please. And when we get into performance-based and we get into how do you apply the standard, if you start reading through it and you start actually applying it, there is a structured approach that lets you adjust the judgments required on that qualitative and quantitative consequences to the public. You can look at how that could be misapplied. Sometimes it is misapplied by just taking everything at the maximum rate. That gives you the maximum in the early stages of the design. It gets applied that way, and that leads to cost and other issues. But sometimes the misapplication can occur in the other direction. They will attempt to limbo under a threshold, and as the design progresses, they find out there wasn't enough margin left. When we have misapplications, when a design takes more than 10 years and a new hazard curve comes out, we have ways to evaluate the significance on that, and we have corrective actions that can be used to restore compliance based off of how much margin you had into it. So you may start off risk informed and you may end up performance based just through how quickly you get through design. All this concept is laid out in an appendix and has been there since 2004. It's very helpful in addressing these questions. Next slide, please. It really focuses on five sub-concepts. I'm going to highlight two of them. The defense in-depth nature of all of the conservatisms you've got in the overall analysis. What are all your design margins? What do you have in quality assurance? How many barriers do you have? How robust is the overall design? It also allows you to look at monitoring releases and emergency planning efforts as you look into the LPZ and your offsite releases, how people evacuate and how you interface with your community. Those are probably the key things that we want to keep looking at, and allowing folks to look at accounting for that. We have restated after the post-Fukushima incident, while this is seismic, if you apply this in the Fukushima example, you had other margins. You had things that had you been able to use all of the different things, you could have relied upon some things differently and mitigated the accident. So we can take lessons learned and say, yes, looking at historical bad accidents, whether it's Chernobyl, whether it's Bhopal, India, whether it's Fukushima, this concept is a fundamental concept that holds through, and you can use the margins to meet your design objectives. The next slide, please. The other portion we want to focus on that gets into the regulator aspect and gets into the subsequent reviews, we want to look at how you address system interaction. We want to avoid common cause failure to the maximum extent possible, and we give various options for doing that, and that allows the designer not necessarily to pick one for the entire plant, but to move system by system based. Depending on what you're getting for certain components, you may choose one of these system interactions more so than the other. Next slide, please. So all that's feeding into an objectives hierarchy. You'll see here, we've got the 5 different columns. They're going to represent those safety design principles and concepts. We've got what are the overall goals. We're trying to protect those 3 things. We've got many different functional performance requirements, and we've got measures and criteria. Measures and criteria on the bottom, when it says binary measures, really you just address that as a yes or no. Do you have redundancy or do you not? Do you have common cause failure? Do you not? You do not have to spend a lot of money and resources looking at exploring that. For the constructed measures that are on here for defense in depth, system interaction, robustness, we have guidance in there on how you look at it. The measure to meet the hierarchy objective through the constructed measure. What is your design margin? What do you have in there? And this overall strategy in the appendix allows you to apply a graded approach. Next slide, please. So if you'll pardon my analogy here, we have the single barrier castle and we have the defense in depth. Which one do we want to incentivize? Which one do you use? Some projects will tell you they want to fix their footprint and they want to have just a single barrier because only one component should be expensive. Well, that doesn't meet our defense in depth goals. You can make that single barrier as robust as you can possibly do it, but it's a trade-off. On the defense in depth concept, we can have high redundancy, high reliability. We can have very low system interaction, which is going to give us a very low risk of a common cause failure. And it gives you the flexibility to respond fairly quickly. In the standard, next slide, please. In the standard, as you're addressing the various different portions for these constructed attributes, for these binary measures, and for each of the categories, you have an allocation and you have an implementation. The allocation is normally done in the design, and that's going to feed into what Brian and then we're going to talk about with ASCE 43. And we have examples on just picking your strategy up front. The Department of Energy uses a safety design strategy in the early stages of a project that's basically going to be an agreement on how the SSC performance is allocated in the design. Once we get through that design process, there's always changes. We have the implementation measures that allows us to go through and make sure that we have met the allocated performance levels and we're meeting the fundamental objectives in the objectives hierarchy. We're still assigning SDCs based off of the most significant negative consequences, and we're moving to being a little more explicit on what some of the risk-informed options can be, but this is the standard as it exists right now. Next slide, please. We have many design alternatives that can be in there to meet the fundamental objectives. We have the natural means, which can be your siting, your distance, your emergency planning zone, your roads, other things that are in the community, preparedness procedures. We have constructed measures. We spend a lot of time focusing on the constructed measures and the specific attributes. And we're, again, with your constructed measures, the standard allows you to grade the approach as a binary true or false statement and not having to spend a lot of time doing analysis. And then we have these proxy attributes, which allow you to meet the means objectives and take some of the considerations on how things are going to interact. The fundamental objectives are generally for protection of the worker, loss of life, for protection of the public, the exclusion area boundary for 2 hours, and for the environment, any large scale, potentially permanent exclusion zones, things like the Thompson 7 and the Chernobyl. That allows you to continue to iterate the design and get to an overall approach. Now, next slide, please. We'll go through an example of where the standard is specifically talking about binary measures and where it needs judgment required. This is the section that's going to go through. Are you using airborne release fractions? Are you using this level of documentation? Are you using this complexity? Or on the judgment side, how much redundancy do you need? What is the common cause failure? A lot of the judgment that we use on the DOE side is order of magnitude judgment. Doesn't require a lot of definition, but you can, on the judgment required side, you can sharpen that pencil as much as you need to as you iterate and agree with your regulator. Next slide, please. So the performance-based approach and the official NRC attributes, they want something measurable. It can be calculatable, but generally something measurable that can be verified to monitor a system. You can look at something to be put in your license. The objective criteria, we do use some deterministic analyses. For tried and true equipment, you can use performance history. But you do have the flexibility to meet how you establish the performance criteria. We're trying to to incentivize various outcomes and encourage the defense in depth nature and the performance-based nature of the overall design. The framework is there to continue to evaluate upsets and deviations that ensure that the outcome does not have any immediate safety concerns to any of the receptors, such that the fundamental objectives are met. This is intended to achieve the highest possible level of safety at a cost without forcing sites to be mirror images of each other. It allows you to tailor it to what you've got and not have a one size fits all. Next slide, please. So the practical implementation of the performance-based approach is really focused on these 5 attributes: something for the auditors to verify, something that is quite objective in how you're going to accept and ensure that your allocations were correct in your implementation. What is the framework for looking at when are you going to worry about systems versus when are you going to worry about components? How are you going to look at your time and energy and physical margins throughout, as opposed to automatically assuming the worst case scenario? The flexibility is there for technology. There is lots of work being done in the working group right now, getting the regulators comfortable with how much flexibility they are going to allow in their own zone, but that is negotiable. And the overall goal here is incentivize the newer approaches, get technology out there faster, reward folks for doing defense in depth, and remove the barriers. So I'll pause there. I know I go fast and it's like a fire hose, but any questions?
I'll start off with some online. So the most direct one was how large is ANS 2.26 now versus pre-RIPB? In other words, I guess there's an assumption that originally 2.26 was not risk-informed performance-based, and then the question is, how much is RIPB, I guess, streamlined or not the standard?
So since 2004, 226 has been performance-based. Where it is going, it is getting larger to basically interface directly with some of the other LMP efforts. I can share where it's going, but it has always been RIPB. The RIPB sections have been in the appendices. And I hate to use a millennial state, but it's TLDR, too long didn't read. And a lot of folks never got all the way into the appendices to realize how performance-based it could be.
Okay. Yeah, go ahead and elaborate, Prasad.
Andrew, I wanted to add to what Doug just said, because I was a member of the first working group that created 226. So before the current version, there was no 226. And, you know, I want to point out that it was always meant to be risk-informed and performance-based. And I've tried to point out every opportunity I have that for ANS, and I believe for other SDOs also, it is the first RIPB standard, as far as I know.
Okay, thanks. Then I do want to kind of highlight a comment from Farshid and maybe get clarity. Farshid Shiroki commented that defense in depth can be achieved without redundancy. And I don't know that you necessarily implied it, but just kind of throw that out there and let either the speaker or someone else comment on that.
So yes, I agree. Defense in depth does not have to be solely redundancy. We can have diversity. We can have the way we do the controls. The overall approach is, whether it's ISA 84 has various different options that don't require redundancy. DOE has a standard 1195, but yeah, redundancy is a common way of meeting defense in depth, but we really like dissimilar methods. One would be fire suppression systems and fire barriers to minimize material at risk in a fuel fabrication facility. There's a lot of things that do not require that redundancy, especially once you get away from power generation into the other parts of the fuel cycle, the recycling, the enrichment, the fuel fabrication.
Thanks. Other questions from the room or online? John Facemire has a question.
So I noticed on the NRC rulemaking website that Appendix S is one of the items covered by the wholesale revision rulemakings. Have you had conversations with NRC staff about ANS 2.26 and in reference to that rulemaking? I know the executive order talked about DOE to NRC transition.
I have not. So we have not discussed that explicitly in there yet. There has been a lot of discussion that the general fundamental principles should not be impacted, and how many reactors do we bring in. Prasad was talking earlier about taking a power plant that was a coal power plant and putting nuclear power in there, and We actually are trying to do that in Oak Ridge right now with one nuclear. And so we are evaluating it and we're probably discussing it weekly, John, but I don't see why it will impact it.
Thanks.
Other comments, questions? Yeah, go ahead. Go ahead, Rich. Yeah, there you go. You say so.
Just a general comment. So I've heard some conflicting statements here. So I've heard 3 times today that we're not waiting on anything. We're not waiting on regulations to change in order to implement the RIPB. But I've also heard several statements where we're expecting the regulation to change. So I guess my question is, if the regulation is fundamentally not performance-based or deterministic, then how do you get past that? Because the regulator has these objective criteria, and you're basically wanting to make a performance-based argument for meeting those. And can you get past that obstacle? Does that make sense?
Yeah, okay. Yeah, I'd like to take that on before, maybe if Raj is still here.
He left when I was speaking.
Oh, okay. Well, maybe Han Fan can respond also. But well, anyway, my response is that, you know, the issue of the functional containment is an example of how an existing regulation can just be interpreted in a performance-based way. In other words, GDC 16, that's the General Design Criterion 16 on the containment, was interpreted for the longest time to be a leak-tight containment, you know, and it was in 2018 that the NRC, you know, put out a SECI paper and the commission accepted it, you know, making the idea of a functional containment to be acceptable. So the point I'm making is that a lot of these regulations have become deterministic and prescriptive through regulatory practice, and not because the regulation itself is prescriptive. You know, in many cases, the regulation is very performance-based in that it very clearly identifies what is the safety function to be fulfilled.
So for this to work, you really require the regulator to really change their approach to how they make these determinations.
Exactly. And I mean, that's the reason why I'm hoping that the regulator will be more involved in the type of guidance that we are developing. But in order for the regulator to be involved, I feel that it is the regulated industry that has to present the regulator with the specific cases where they have used the performance-based approach, and the NRC is then forced to review it in a performance-based way.
One follow-up comment I have. So in your presentation regarding strict configuration management, and I understand the benefits of that. I'm not really arguing against that, but I'm having a hard time understanding how risk gets factored into that process, because what developers have really want is they want to be able to concentrate their resources where they're most needed. So by quantifying the risk associated with different aspects of a system, you can basically spend your resources on those higher risk aspects and reduce the resources required for the lower risk aspects of a system or portions of a system. And I'm having a hard time seeing that in the process that you displayed on the slide there.
Well, all
Where
I
does the
can say,
risk, where does the risk come into that? I understand, because you did make a statement that if the regulator changes its requirements and reduces its requirements, then that all filters down in, and you can basically, you wouldn't be knowledgeable of that through your requirements analysis. I understand that. I understand you can reduce that, but that's all dependent on them changing their regulations. Where does risk come into this? I'm not seeing that.
well, what I'm suggesting is that you don't need to change the regulation in order to be able to make use of existing margins. So I have to refer you to the guidance document developed by ANS for RP3C, in which I tried in one of my slides to say, what are the risk-informed attributes? What are the performance-based attributes? And if you looked at the performance-based attribute, it refers to margins. So the idea is you don't even need to go into risk, which involves failure of SSCs in order to have radiological exposure. So you just stay on the side of the system state where it is successful, and you work within the margins allowed for success, and you say that you never reach this point where there is failure. So you have a choice in RIPB to work either in success space or in essentially failure space.
So your message is not that implementing strict configuration management control is reducing risk. That's not your message.
No.
Okay. All right. I'm still having a hard time figuring out how this accomplishes a graded approach, because it seems to me in the process you laid out there that your requirements are the same regardless of what the risk level is for those parts of the system. I don't see the risk coming in to control what gets traced and to what degree.
I think to answer your question, we'll have to get into some specific use cases, where we'll have to deal with both.
Okay, thank you.
We are willing to do that. So.
And we have Ralph Hill. Ralph Hill has had his hand up for a little while. So Ralph, let's try this out again and see if we can hear you. Go ahead.
All right, can you hear me all right?
Oh yeah, loud and clear. Thanks, Ralph.
Okay, thank you. So in the plant systems design standard addresses your question. We integrate the design process from early design through preliminary design to detailed design with risk evaluations in each of those design phases. So you evaluate your early risks, you allocate those down to systems in the preliminary design, and the system design, and then component design, you allocate the portion of the system risk that the component contributes to the system risk. And you evaluate that through, and we don't just look at it from safety risk standpoint, we also look at it for productivity. We evaluate the things that can cause a system or a plant to be unavailable. And then we optimize, we have a process to optimize between the safety risk and the unavailability risk. Obviously, if a plant goes down because it's a safety component, it's still also unavailable, but there are things that can cause a plant to be unavailable that aren't safety risks. So we account for all of those in the plant system design standard. And since it's done over the design development process, you can, if there are changes in requirement, and you've got good requirements management, if there are changes in the requirements, you capture those, and those get in a good requirements management system. You identify what systems and components are affected by that change in the requirement. It's pretty straightforward.
Ronnie, did you want to make a comment? Want to add anything to this? Okay. Well, we're at 2:15. A very good discussion, but let's give everybody a break, and we'll be back in 15 minutes at 2:30 p.m. Eastern Time. So thanks, everybody. We'll be back. If folks could move towards their seats. Going to have two good-looking gentlemen, one of which is George Clooney, present. I didn't know that he was going to be here, but I guess, you know, that's. Oh, and Sean Connery. Oh, excellent, excellent. So let's go ahead and get started. This is the last session. So we're going to continue on the theme of RIPB for civil structures. And I think this is another great example where we're going to be speaking to an actual standards merged maybe into one standard and an actual application of risk-informed performance-based. So take it away.
Very good, thank you. Yeah, so I'm sure you recognize this from our photos, and after this is done, if you ever need to pick us out of a police lineup or something, you'll remember what we look like.
Brian, you changed.
That's the picture I use on my dating app. So.
As opposed to the one at the end of the day.
Yes. So I pressed forward. I'll press it again, even though I was told not to. It's taking much longer than 3/4 of a second. So I think we'll. Oh, maybe it's the. I'll press backwards. See if that works. No. Yeah, we thought we had graduated, but oh, okay. I think it's this. Okay, I think I understand that. Of the 5 buttons, I was picking the wrong 3. Yeah. Here's where we are now, middle of the afternoon. I do not want to kill anyone by boredom with more PowerPoint. If this session is me droning on to you about civil structures, I have failed. So I really want to get feedback. We really want to field complaints from in person and online. We have 2 things to talk about, both related to RIPB of civil structures. Now, I know a lot of nuclear SDOs are pivoting to RIPB. We're not. Why aren't we? Because we're already there, and we've been there since the mid-1990s, and it's worked really well. That might sound like I'm bragging, but I'm really standing on the shoulders of giants. So I want to show you what we do for RIPB for civil structures, and hopefully you can learn from the many mistakes we've made in the last 30 years. And then the more important part of this talk will be given by Andrew Whittaker, and that is RIPB gives us an opportunity to right-size our standards. And so we are working hard to do that with ASCE 43. And Andrew's going to show some descriptions of how you can eliminate the zombie prescriptive requirements from your standard. And then after that, hopefully, like I said, we'll have a conversation. If not, maybe a nap. Uh-oh, I hit it twice. Oh, maybe I do want to hit it twice. No, now it went on. Help. You can go back into presentation mode. I will hit this once. Wow, this is really working well. Can you advance the slide, please? All right. So as we've heard all day today, RIPB is in the eye of the beholder. There doesn't seem to be standard definitions that all of us agree on. Here are my unofficial definitions from the perspective of a structural engineer who is designing structures that hopefully won't collapse on your high-tech plants in an earthquake. These are very consistent with what Ronnie showed earlier with the orthogonal axes. Performance-based, you can read it. I'm not going to read it to you. Basically, let the engineer do his job to give you a building that's going to perform the way you want it to perform. So we want no damage in the worst possible earthquake, a biblical earthquake. Fine, we can do that. We can tolerate some damage in a more moderate earthquake. We can do that too. Performance-based design is actually something in the structural engineering world that we have done for decades, and we've done it outside the nuclear profession. And the example I like to give is when we specify concrete for a building. Back when I first started in the 80s, we used to put in the specifications how many sacks of cement you use per cubic yard of concrete, a prescription. And then the contractor has to follow that prescription, whether it's a good prescription or not. Now we say, hey, contractor, we need concrete that's got a 7,000 pounds per square inch compressive strength. And it's got to be durable. Your aggregate has to meet these ASTM requirements in grading. Go out and find a good concrete mix that does that and give us some paperwork that shows you've used this mix before or you've tested it and it works. So we push that to it's a performance specification now for the contractor. We want concrete that's this strong. You figure out how to give us that concrete. So over the decades, we've switched from a prescriptive, almost all specs were prescriptive for concrete. Now they're almost all performance-based concrete. So for an engineer, for designing nuclear structures, you have to, you let the engineer do what he does best. So that's a performance-based design. You tell us, and I'll show you an example in a second. Performance-based design can, or maybe not, be risk-informed. So when you tell a structural engineer, I want the building to be only have moderate damage in an earthquake that comes around every 2,500 years. That can be deterministic. You know, that could be just something made up because that's what everyone's done forever. Or it can be something that somebody's figured out. How much damage can we tolerate? How much risk can we tolerate? So we'll see how how that works as well. And again, there's analogies in structural engineering history. We used to design buildings for take 7% of the weight of the building, apply it sideways. That's how you design for earthquakes. That's a deterministic load. We've gone well beyond that, both within the nuclear world and commercial world. Next slide, please. So risk informed. I'm gonna go back. The risk informed comes first. This is Doug's domain. So Doug just talked about this, and there's two bits of information that come out of ANS 2.26 that I, as a structural engineer, need. So start on the bottom, a limit state, a damage limit state. So this is stage design. This you can see the structure as you go from left to right, gets more and more damaged. So you have to think for this particular component or this particular structure, how much damage can I tolerate before something horrible happens? And then you go, and something horrible in this case is going to be a dose at the, say, the exclusion boundary. So for any of those damage states, how much dose are you going to get, and what kind of tolerable frequency do you have? That top thing is from NEI 1804, 408, something like that. So like I said, this is not the domain of a structural engineer. Somebody smarter, higher on the nuclear food chain does this sort of work. So click for the next. So for instance, you know, for any particular SSC, they might decide that limit state, the third one from the left, is tolerable. It'll give this much of a dose. So the dose is increasing from left to right, and the frequency, allowable frequency, think of that as a yearly probability of occurrence, also goes down. So the more dose, the less tolerant you are of it. The lower the frequency has to be to maintain that risk. This is risk informed. So somebody's thinking about this and saying, okay, I can give the structural engineer these two things and have them design a structure that meets this. So if you click again, now we get into the realm of structural engineering. So the top graph is a hazard curve, seismic hazard curve. Intensity increases left to right. So for high intensity earthquakes, biblical earthquakes, they happen luckily with very low frequency. You know, things like buses driving by happen with high frequency. That graph comes from God. We can't do anything about that. That's the site seismicity. Wherever you're going to build a plant, it's going to have a series of curves like that. What we can do is design a structure that has a certain called target fragility. And that's the bottom graph. So the bottom graph is the same intensity measure, you know, spectral acceleration or peak ground displacement, whatever you want to use, from increasing from left to right. Then on the vertical axis, is the probability that you're going to exceed the limit state. So The higher the intensity, the higher the probability of exceeding the limit state. We know the two ends of that graph: zero intensity, zero probability of exceeding the limit state. Biblical intensity, 100% chance of exceeding the limit state. And then you pay a structural engineer about $1 million to get out his crayons and draw the curve in between those 2 points, which I'm happy to do. But in the end, that equation on the bottom is an application of total probability theory, and we can calculate how often that damage state is going to be exceeded based on the site seismicity. So if you click again, two pieces of information: a description of the damage and how often that damage is tolerated. Risk informed, and then we do a performance-based design to get a structure that looks like that. So next slide. Oh, okay, sorry, stop here. I forgot this. So this is a repeat, but the big box on the left with the red shading, that's, like I said, that's done by people that know a lot more about this than me. That's done by the owner or the regulator. Risk informed. Performance-based, that's where I'm happy. That's my sandbox. I can give you a structure that meets those two criteria. Next slide now. So this is our document. It is now going to, it's a combination, it will be a combination of ASCE standards 4 and 43. It's going to be actually called ASCE 92. That might be a number that's familiar to some of you on an atomic scale. And this has what I was just talking. This is a standard that shows engineers how to do that performance-based design, given the criteria, the risk-informed criteria from ANS 2.26. So if you click again, these are documents from the other side of the wall. 2.26 is there. I imagine there's going to be the same thing from the NRC and maybe from other sources on how you select, how you do this risk-informed selection of damage state and frequency. And then if you click again, this is these are the ASCE standards. So there's been some talk about standards getting longer and longer. We're as guilty as anyone else about that. We are not going to recreate every requirement for how much rebar you put in here, how you bend the rebar, all that kind of stuff. That's already done by our colleagues. I'll point out ASCE 41 is a performance-based standard for design in commercial space. Now, in the early 90s, when we put together the performance-based requirements for nuclear structures, that was in it. They were both in their infancy. They were kind of based on each other. Now, ASCE 41 in commercial space, I don't think I'm exaggerating if I say there's been 1,000 times more structures designed for that standard than our standard ASCE 43. There's just a lot more commercial structures out there being retrofit and designed. And I don't think I'm exaggerating saying there's 10 times more engineers working on that and 10 times more academics doing testing for that. It's, we used to be the best at this, no longer. ASCE 41 has passed us by, and it would be negligent of us not to bring in those commercial standards into our standard. So I think that's all I wanted to say with this slide. This has all been pretty academic. If you can, click past this. We already talked about that. Here's just a very specific example. Let's say you're designing a concrete box that's going to house something on your plant. And somebody smarter than me says, well, I think we can tolerate a little bit of damage here. Let's call it limit state C. So this is, some not quite negligible, but moderate damage. Based on my calculations, which you can talk to Doug about, that looks like maybe 50 rem at the exclusion boundary. You go up to some curve that's based on NEI 18-04. You say, okay, that's an allowable annual probability of exceeding that, or annual rate, kind of equivalent with these low numbers, 4 times 10 to the minus 5. So risk informed. Click again, please. This is out of Doug's standard, 2.26. There's a seismic design category that you pick. One of 2, 3, 4, or 5. 4 happens to be 4 times 10 to the minus 5 here. Arbitrary. It could be a sliding scale. It doesn't have to be one of those 4. And then limit state C. Excuse me again. Limited permanent distortion, minimal. So You come out of 2.26 with those two numbers, and you walk across the street to the structural engineer's office. Click, please. And you give your structural engineer those two numbers. Now this is a graded design. You know, as the probability of failure goes down, your design becomes more robust. So you can pick any of these to get the robustness you want that way. And also as the allowable damage goes down, your design gets more robust. So I think John was saying that 43, when used for light water reactors, was not quite performance-based design, because you always pick D, you know, stay essentially elastic, and you always pick seismic design 5 as it was the highest two categories here. But you can pick any of those. So that's the graded design. I think maybe, Richard, this goes to your question just prior to this talk about how do you pick the risk? How does the risk get in there? This is how it does in this case. Next, click, please. So ASCE 43 then gives you the design loads on the structure that will meet, remember the target fragility that I showed before, that will meet the performance requirements. If you click again, comes in the form of a safety factor on the uniform hazard response spectrum here. There's an equation for that in the code. All of the performance-based is now built into it, such that when you design to this safe scale factor, you will satisfy that equation. So that's transparent to the designer. It looks like a prescriptive requirement because we have to simplify things for you know, we engineers aren't all that bright, so we don't want too many numbers. We don't want to be doing integrals. So we make it look prescriptive, but it's really all built in. Click, please. So this is the conclusion of my part. I wanted to convince you that we know what we're doing with RIPB. We've been doing it for a long time. We only need really the two pieces of information. What's the allowable damage? How often can you tolerate that? And the other thing is, how to do that shouldn't be prescribed. We shouldn't be telling contractors to use 7 sacks of cement in their concrete mix. We tell them, you know, when you build this building, we want 7 KSI concrete, and we want aggregate that's not susceptible to ASR and all that kind of stuff. So, and then what Andrew's going to talk about is that last sub-bullet is opportunities that this gives us. If people are truly committed to doing RIPB, it allows you to right-size your codes and to make things easier for everybody, as long as we're all on the same page here, which is why Doug and I have people on each of the committees to watch over to make sure 2.26 and what's going to be ASCE 92 play nicely together. All right, I'm going to go take a sip of water. It's all yours.
Thank you, Brian. So I'm Sean Connery, and I'm happy to follow George Clooney. But the second part to this talk is about right-sizing requirements for nuclear civil structures. Next slide, please. So as we write ASCE 92, pivoting away from 4 and 43, we recognise that in nuclear energy space, beyond DOE space, that our scope or our remit has changed. And so as we write this standard or update the standard, we recognise we need to accommodate gigawatt scale reactors, limit state D, seismic design category 5, but also moving through the micros, bottom left, through the advanced reactors, small modular reactors that I associate with the Natrium build for TerraPower and GEH, through to a different application, top right, of nuclear energy, where we're using, in this particular case, high temperature gas reactors to support the production of synthetic hydrogen. So this is a very different application than the one bottom right, a gigawatt scale reactor. So as we write this standard, we've got this expanded scope to deal with, and we recognise we're dealing with an expanded scope. Next, please. So not lost on me, not lost on Brian, and I think not lost on anyone in this room is the scope of our enterprise going forward. So as we think through how we right-size nuclear civil structures, recognising at the moment that the civil structures part of a nuclear plant represents 55% of the total cost. and we need to get that back down to about 20% of the cost of the asset. We have a rate of deployment that's unprecedented. So what we've done for the last 25, 30 years is not going to work for us going forward. So we need to think, how can we speed the deployments, maintain the safety? So we're focused on this DOE goal. This is an image generated by Robbie Stewart from Alva using data from the Loans Program Office of DOE last year. So this is the deployment that we're thinking about for the range of reactors presented on the previous slide. Next, please. So to build on the discussion about high-performance civil structures, what are these non-nuclear civil standards that we might start to lean on? And they're listed here. These are the commercial standards that are updated on a very regular basis in the United States, typically a 5 or a 6 year cycle. And these deal with typically, well, here they deal with reinforced concrete and structural steel. There's the standard ASCE 41 that Brian introduced a few moments ago, and there's ASCE standard 7 that Doug touched on. This is a standard for the design of buildings. I recognize that nuclear structures in some cases have what I'll call irregularities to accommodate nuclear kit that would not be acceptable in a standard building structure. So the blind application of ASCE 7 to a nuclear structure will not work. It has to be a little more thought beyond ASCE 7, and that might embrace ASCE 41. So non-nuclear standards deliver what? Well, they deliver limit state A, limit state B, limit state C, limit state D. We just don't call it limit states A, B, C, and D. And we've been doing that for 65 years or thereabouts. As Brian pointed out, we've had performance-based seismic design since we started work on that in 1992, and we stood on the shoulders of academic work done in the United States and abroad dating back to the 1970s. And we delivered defence in depth. We don't make a song and dance about delivering defence in depth, but we do deliver defence in depth by requiring our framing systems to be redundant, which is defence in depth. What do our nuclear standards, our nuclear materials standards deliver? We have ACI 349 and AISC N690. They deliver limit state D. That's it. There's no allowance for limit states A, B, or C, which it kind of obliges ASCE 92 to embrace the non-nuclear standards to ensure that we can deliver across all 4 limit states. Next slide, please. So what are the proven ingredients for a quality civil structure based on US design experience? They're listed here in a bulleted list. I'm going to touch on just a couple of them with standalone slides, but having an experienced design team with proven construction experience, i.e. they've built things, is key. Early engagement with a contractor, a good contractor. Peer review, an understanding of what's important in terms of materials. Brian touched on this a few moments ago. I'll talk about detailing of structures, which is key to delivering quality. A complete set of construction documents, which in the past has been unusual for the nuclear industry. You would be run out of town in non-nuclear space if you tried to get a price to build something complex without a complete set of construction documents. Then I'll talk about construction supervision and special inspection. But the most important bullet here is the last one. Nuclear is not special. We might like to think it is. It's not, at least in civil structures. It's just another building. And we've got to start thinking like that. Next slide, please. So, concrete. Everyone has some understanding of concrete. And I think someone mentioned testing concrete, and we have a standard test that's been around for many, many decades called a cylinder test. And most folks don't realise it's a test for quality control. It's not really a test for concrete strength, despite what some people think. But the fact of the matter is, if you follow our non-nuclear material standards, And that's in the United States. So there are the similar standards in Canada, similar standards in Australia, where I was born, similar standards in the United Kingdom and Europe. You will have in-service strength that will always exceed the minimum specified compressive strength, kind of guaranteed. Yet we tend to wring our hands and worry about this value of F'(C), the concrete strength. So I asked the question here, is it important? Would a 25% reduction in concrete strength affect the shear strength of a beam, a column, or a wall? No, the effect would be insignificant. Would it affect axial strength? No, not really. And indeed, Richter at the University of Illinois Urbana-Champaign figured this out in 1930 and developed some rules that still exist in ACI 318 to address this. And in terms of deformation capacity, a 25% reduction in the concrete strength might actually increase the deformation capacity of components, not decrease it. So we tend to focus on the things we're comfortable with. We don't necessarily focus on the things that are important. Next slide, please. So I think everyone needs to understand that if you want a high-performance civil structure, you need to pay attention to the construction details. And the images at the bottom supplied to me by Fred Grant from SGH for a presentation at the NRC last year is of a similar construction detail, a beam to column connection. And I think you probably, I'll let you take your pick, which one would you prefer? The one on the right was designed by and detailed by a colleague of ours who's in the National Academy of Engineering. The one on the left. The one on the left. The one on the left. The one on the left.
That's what you call emphasis.
That must have been Sean. That must have been Sean.
Every other. Stay, everybody. Take a break. I think there's a mute. Hole.
Could be heard. All right. That's a Sean problem, not an Andrew problem. So the point here is that
Try again, Don, see if it's still doing it. Maybe somebody, I think someone online.
Hello?
Great.
Can everyone on, ask everyone online to go on mute.
if I'd had the mic, I would have followed up. Hello. Anyway, the point here being that these are two nominally identical construction details. The one on the right is well designed, well detailed. The one on the left looks a little like my son's dog's breakfast. It's a mess. You can't place concrete. You certainly can't vibrate concrete in the detail on the left. The one on the right is well detailed, and that's the quality you would expect in a well-designed structure. So again, it's not really the concrete strength, it's not the reinforcement strength, it's the quality of the engineering. And how do we ensure high quality engineering? Well, we'll touch on that next. Next slide, please. So how do we deliver quality before construction? We call it peer review. This is standard practice in non-nuclear space for performance-based seismic design. It's just obligatory, and it's worked well for about 30 years. So delivering quality before construction, you touch on all of those bulleted items. And the goal is to ensure that you develop a set of construction documents that map to the detail on the previous slide on the right. It's standard practice. We've been doing it for a long time. We know how to do it. It's a positive process. It improves the quality of a design. It doesn't slow the design process down because it proceeds in parallel with the design. How do we deliver quality in the field? Non-nuclear space, there is a requirement that there will be what we call structural observation by the engineer of record. This obliges the person that signs off on the construction documents to spend time on the construction site, ensuring that what the contractor is delivering maps to the construction documents and the intent of the design. So there could be some minor deviations from what's shown on the construction document. The engineer of record is well positioned to say, is that acceptable or not? It's the role and job of the engineer of record. In California, where we implement performance-based seismic design, where we design mission-critical structures such as hospitals for fairly long return period earthquake shaking, there are special inspections by qualified personnel. It is a standard regulated process and it works. And we also know how to do seismic qualification of components and equipment on the west coast of the United States. For mission critical infrastructure, you're by and large obliged to use seismically qualified non-structural components and systems, or what some have called SSCs. Next slide, please. So as we think through delivering quality in ASCE 92, NQA1 was not written for civil structures. In fact, it's a stunningly poor fit for civil structures. So our current plan is to dial back to Appendix B to 10 CFR 50, and there are 18 items to be addressed. And about half of them are related to civil structures. So we plan to address those, probably about 8 or 9 that are applicable to civil structures directly by pointing to construction practice, codes and standards in non-nuclear space. Why is that sufficient? Because we've been delivering high performance civil structures in non-nuclear space for decades. So we think this is a speedier pathway to delivering more than sufficient quality within the framework of within using existing standards, non-nuclear standards, but also recognising the role of Appendix B to 10 CFR 50. So we need a mapping. We think we have a mapping. Next slide, please. So this is a slide generated for one of my colleagues in the room. It talks a little about seismic hazard, credible and incredible. We've talked about elimination of one incredible hazard a little earlier today with aircraft impact, hopefully moving off to one side. Another topic we're going to think a little about is incredible earthquake shaking. So these are seismic hazard curves generated from a USGS tool, and it presents data out to return periods of the inverse of 10 to the minus 16. So we decided to attach mean return periods to the last ice age, the age of the Grand Canyon, and then the age of the universe. So as we start to think about risk, to go back to Brian's example a little earlier, we generate seismic hazard curves. This is a family of seismic hazard curves. We integrate a fragility function over a hazard curve. We compute risk. As we think about risk, we need to, in my opinion, start to think about risks that are plausible. When we get off into 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, it's kind of hard to wrap your head around a risk number that is that small. So something we're going to work on and think about and talk about over the next year. Next slide, please. So conclusions for part 2. We ought to leave the performance-based details to the SDOs. And I think Brian touched on that in his remarks. To meet the goals that we identified for the advanced reactor build-out, that's the image generated by Robbie Stewart, we're going to have to streamline a process to design, license and deliver these plants. So we need to think about the problem differently. And for civil structures, the RIPB framework is set. As Brian said, we know what to do. We need input from others to help define the limit states, to identify the target performance goals or the seismic design categories. Given that information, we can deliver a building design. And we anticipate that there will be changes, significant changes in ASCE 92 with respect to ASCE 43, with respect to QAQC, whether or not we need to deploy what we call soil structure interaction analysis, when site-specific hazard calculations are needed, and perhaps when we can pivot to the USGS tool. And the focus here is to speed deployment, but not compromise safety one little bit. And I think the last slide gets back to an important topic of defence in depth. No, second to last slide. So no death by PowerPoint. I think we've achieved that goal. We'd like to now have a conversation where you ask questions of Brian and me about anything related to civil structures, but I've seeded the discussion here. So what didn't we talk about? We've talked about a little about ASCE and risk-informed performance-based design, how we harmonise across the SDOs. A number of us have talked today about how do we stay in our swim lanes so we don't lead to conflict between the SDOs, that the SDOs can work together efficiently. And then one important point here is integration within the disciplines. So within our discipline of civil engineering, we have the ASCE standards, we have the ACI standards, and we have the AISC standards, and we don't yet speak the same language completely. So we need to do a better job within our discipline in order to deliver on risk-informed performance-based design for the industry. Now, the last slide deals with a really important topic of defence in depth, and it's meant to foster some discussion going forward. And you see what happens to Sean and George. So when Brian and I are thinking about how do we talk about defence in depth, well, it was when I was a young boy, which is a long time ago, it used to be called belt and suspenders. And the chap on the left, if that belt fails, we have a wardrobe malfunction. The chap on the right, his belt fails. Let's hope that his suspenders are seismically qualified, or at least weight qualified. So with that, we'll take questions. I don't know, Andrew Sowder, if you want to moderate this. Be happy to let me to.
Well, I was just going to start off with an observation or comment online, and there was response as well to the point you made, which is, and I think you knew you were going to get a response. Someone online is disagreeing and saying, well, nuclear is special, and the statement is because of radiation hazards. But someone else online pointed out that the issue is, you know, radiation is another hazard, but there's other ones that are commonly designed for in commercial structures as well. So I just wanted to fill that out and let you maybe spawn back.
Yeah, I think it's a good comment. What's different about nuclear? And I will point the person who made that comment back to the slide that showed the graph from 1804. That's specifically set up for radiation dose and release of radiation. And you can go to the graph and pick out what margin you want. We used to call them safety factors, margins. But basically, what is your tolerable annual probability of failure, a probability of exceeding the limit state that might lead to that failure. So it is built in, and it could very well be that if there's a possibility of a large release of radioactive material, then you'll be designing to limit state D and SDC5 like we did with all the old light water reactors. So you can pick your risk. You can inform your engineer of that risk.
Normally we disagree on everything, but this time around, Brian, I agree with you.
Must be wrong.
Yeah, it's Mike Milton. This is great. I don't know. I also agree with that comment. I mean, if you were my contractor, I'd want you to I'd want to hear from you that nuclear is special going in terms of a safety culture as we do business. And while we may be fueled by trisol fuel and, you know, looking at a functional containment, and maybe we just need a reactor building to, you know, maintain a vacuum or, you know, functional, you know, everybody at the table needs to understand nuclear is special. So
Quiet. Please finish. Ignore him.
You guys are great. My other comment is I see all that rebar and I see expense, you know, money. So, you know, where are you at? I mean, I used to work at Palo Verde and I was involved in tendon inspections, and it was pretty darn special with those tendon reinforcement, with the domes, you know, and maybe that's going to go away. John says maybe there'll be a change.
I'm going to have a go at that before I hand the phone over.
Where are you at? And yeah, technology wise, inexpensive concrete building design now, you know, with alternative ways instead of having to have massive rebar. And we don't want to build all that in the field. We want to build that in a shop somewhere and ship it. So where are you guys in all that?
All right. So you can clean up my mistakes. The engineering, think back to the two images that I showed you. Which one did you like? The one on the right. Less rebar, well detailed, carefully thought through.
No, I didn't like that at all.
Yeah, you want no columns, I get it. But the point is, you can have brute force design, and it generally doesn't work particularly well, or you can use more elegant design. But the engineer, the person that designed the connection on the left is not of the caliber of the person that designed the connection on the right. If there had been rigorous peer review, the detail on the left would have been discarded, set aside. The one on the right delivers quality at a much reduced cost to the one on the left, which is unbuildable. So that's part one. Part two is we are working on how you enable, say, the use of precast reinforced concrete. ACI 349, for no good reason, doesn't permit it. ACI 318 for building structures, limit states A, B, C, and D, has permitted it since 1999. So the pivot to the non-nuclear standards is going to improve options, ensure that the design is modern, and I think lead to much lower cost, higher quality civil structures. Now, correct what I've said, please.
Unfortunately, I agree with everything you said. But at the risk of being glib, I want to go back to nuclear is special. Nuclear structures are special. A, see NEI 18-04, and B, well, special compared to what? How about the neonatal ICU ward in a hospital? Is it more special than that? Or you know, we don't want those babies to have something fall or collapse on them, or have the hospital have to shut down because of an earthquake. So we design to the highest standards for earthquakes. Every high-rise building in the last 20, 30 years in San Francisco has been designed using performance-based design. They all violate the building code, but they violate it because the engineers have shown that this system that they're using is actually better through testing and through nonlinear analysis. So they can show that it exceeds the intent of the building code, even though the concrete shear walls are taller than the code allows. So yes, nuclear containing the radionuclides or whatever they're called is important. But there's other important things out there too. High rises in hospitals being two of them, and we design those all the time.
Just a couple of comments.
Hang, Mark, sorry.
Yeah, okay, a couple comments. I want to follow on there with your comment about the nuclear being special. And, you know, I think that's something that we've heard for many decades. And I think for a long time it has been true, because the approach that is still applicable today has built an industry that's been, you know, relatively safe. But I think the idea that we will continue to get high performance using a compliance-based approach rather than one that is risk-informed and performance-based, to the point that you just made about structures that aren't compliant with standards but outperform what the standards would essentially create a ceiling for, in many ways, looking forward, is going to limit or inhibit innovation. And we don't want compliance to inhibit innovation. So I think we need to be open to looking at and incorporating best practices that are deployed in other industries, petrochemical, aerospace, just to name a few. They have safety critical outcomes. Use the example of the neonatal intensive care unit. It's another good example. There's many that are. So I think, I think we need to maybe widen the aperture as an industry and think more objectively and with a larger open mind towards what it is we're really trying to do and what really is the basis for safety and where that high performance comes from. So that I'll go off my soapbox. That was my comment. And now my question. Earlier you had talked about Part 50 Appendix B not being a good fit for civil structures, and that you
not being a good fit.
Okay, and that you made some mention about mapping non-nuclear codes and standards to the 18 criteria or vice versa. Could you go back and maybe just put a little more color on that?
I think the shaded yellow was the color. If we can go back a few slides. So the goal here was to identify what parts of Appendix B relate to civil structures. And it's a relatively small fraction of the 18. Those we want to tackle head on and use very best practice in non-nuclear space, such as that used to design hospitals, offshore oil and gas platforms, mission critical infrastructure, risk category 5 buildings, defense related here in the United States. Those standards are sufficient to deliver high performance, and that's what we plan to lean on. That's where we have a large body of experience. It works. And so that's the thinking.
So a couple things, well, just one thing. When we first started to have the idea that we wanted a chapter in our standard that applied to QA and QC of civil structures, we talked to people at the NRC about this, and sort of the consistent message we got back was, hey, you just have to meet the intent of the appendix, meet the intent of the appendix. So our goal then starting off was, okay, we will write a chapter where we map to the 18 parts of the appendix and show that we meet the intent of each and every one of them.
Other questions? Well, I think Suresh, we chopped you off.
My simple question was, you mentioned that, some level of radiation release is acceptable as part of this thing. Can you explain that a little bit more?
Slide 5, please. There you go. We'll advance one more. Nope, yeah, you can leave it right there. So what I said, people that are smarter than me and higher in the food chain does make those big decisions. But what I understand from the little bit that I could absorb from NEI 1804 is that I think this answers your question. This is something I pilfered from 1804, and it shows that, for higher doses, your tolerable release goes down. You say, oh, linearly, this is log, so it goes way down. So if you have a structure where a little bit of cracking might release a lot of a material, you are going to be designing for a very, very low probability of failure, something way beyond design basis for regular nuclear structures. And I think this goes back to the other question, what makes nuclear special? This makes nuclear special. We will, if there's a chance of a high release, we're going to be designing a structure that has very little probability of suffering damage, even in a biblical earthquake.
Just to go back, a nuclear building is not special per se in terms of it. It's not an intelligent structure. It doesn't adapt to suit its environment. The point here being that, as Brian pointed out, you pick a limit state based on acceptable damage at a given mean annual frequency of exceedance. That is input to our process. Once that's input to the process, what the radionuclides are is not relevant to the design of the building. So if you look at the ASCE standards, we don't talk about radionuclides. I guess if I can go to some ANS standards, they're not going to talk about mixed designs for concrete, staying in our lane. So the point here is we design mission critical buildings each and every day. We know how to do it. And other types of buildings, other types of structures, offshore oil and gas platforms, they have different metrics of success or failure. They use a very similar approach, and they've been using this approach for decades. You might say, why? Because it was the same folks, Alan Cornell at Stanford, amongst others, that developed these risk-based approaches starting really in the late 1960s. So the thinking is not unique to nuclear. Design of buildings is not unique. Design of high performance and construction of high performance buildings is not unique to nuclear. That was the comment about nuclear, quote, not being special. Radiation release is unfortunately, well, fortunately or unfortunately special. I get it. But the design of the building, it doesn't recognize a REM dose at an exclusion boundary.
Thank you for the presentation. I just want to weigh in on the nuclear is special perspective. I just want to weigh in on the nuclear is special or not special debate, because I find it interesting that it's been described this way for a long time. And I think it's described this way in part because of its origins. So mutually assured destruction is special. And it was for a long time in the Cold War, a concern. But the nuclear industry has what I would consider to be unique hazards. All industries have hazards. The nuclear industry has unique hazards. Flying has different hazards. People do it every day. NASA takes on similar hazards to put people in space. Human life is on the line, and it has been lost, but it has been considered acceptable by society to pursue knowledge of space. And so I think we need to look at nuclear in a similar way. It is like any other industry with its own hazards. Nuclear's hazards are unique. Other industries have their own unique hazards. That's just my perspective.
Let's see, my take on the question of what makes nuclear somewhat special is just in the way we deal with the risk aspect of it and the performance-based aspect of it. The risk aspect of it is taken up by the tolerable radiation doses that are delivered, because that is basically a risk calculation as to how much radiation is okay to release. For example, molten salt reactors will have substantial amounts of radioactivity released as part of the normal operation, where the fission gases are separated from the fuel. And those have to be contained, but there are going to be normal levels of radiation release. Even with our currently operating reactors, there's normal amounts of radiation released. So I think that is part of being risk-informed and performance-based, is that we accept certain levels of this hazard, and we know what the consequences are, and we present the arguments to the decision makers on why it is okay to proceed with this valuable technology. Now, the performance-based aspect of it, to me, is entirely based on margins. That was one of the slides I showed. You know, if you want to go to a performance-based approach, you have to know what your margins are and how much of the margin is really necessary in order to make sure you avoid having any release at all. Now, and you know, that's where the limit state of a system-based approach defines the limit state such that you always have margin to release. In other words, you never get closer to this limit state than you have to in order to make sure you are successful in your project. So to me, the idea is you begin with the decision-making structure where you're able to accommodate the hazard as well as the degree of performance that will keep the hazard within tolerable limits. And you know, that sort of argument is exactly what I think NASA uses in what they call the assurance case. And I'll let Bob Youngblood tell me if I'm wrong on this. But you know, what we call presenting a safety case to the NRC, we should be able to say, you know, what are the claims we are making, and you know, what are the arguments in favor of those claims, and what is the evidence we can show, and that is performance-based.
Thank you, Prasad. I think this is a really good example of how performance-based means different things to different SDOs and to people worried about different parts of the plant. If I understood what you said performance-based has to do with margin. So we get some kind of risk-informed lambda from the left side of the slide, and then we designed some kind of margin to ensure that never occurs. That's not what happens in structural engineering. In structural engineering, we assume, and sorry, people online, I'm walking up to the board and pointing to the top left diagram again from 1804, that smart people will tell us what the tolerance for a release is, and we design to that. If we build 1 million of these structures and we monitor them for 1 million years, if we've done our job right, and you go back and track all the releases over time, you'll hit this lambda. You're not going to hit 0. We're not adding more margin on this. We're not saying, okay, give us lambda, and then we're going to apply a safety factor such that lambda is 0. First of all, not possible. Second, that would be disingenuous of us. We want to hit this lambda. We want to build efficient plants. You tell us what lambda is, and we'll give you a building that meets that. One other thing I wanted to say, based on something I heard between lines in a question earlier, is this peer review of the design and site inspections being important. If you were to reverse engineer, take all our performance-based design knowledge, reverse engineer from the building codes what the rate, what lambda would be for failures of buildings and bridges in the United States, you will find that they actually fail about 100 times more, maybe even more than that, than what you would calculate if everything was done per the building code. Why is that? Human error. And there's a great study done by Andre Novak at University of Michigan that shows, 90-some%, put the second figure wherever you want, of failures are due to human error. How do you eliminate human error? Peer review the designs. Get the structural engineer out, make him put his boots and his gloves on, get him out at the site to look at what they're building to make sure it looks like what he had intended, he or she had intended, sorry. So that's why in ASCE 92, we are kind of pivoting from other quality measures to emphasize the peer review in the field inspections, field testing. Andrew said something very bold. I thought you were all going to throw things at him and boo him when he said that there's 0 chance that we're going to get concrete strength lower than what we specify. how can he say something that, how do you know? Well, because when they're pouring the concrete, a guy comes up with a wheelbarrow and says, okay, pour some of this into my wheelbarrow for me. And then they go test that concrete. And I was involved in a nuclear structure where the day got hot. They had a number of mixed designs approved. It got hot. The concrete started to set up too fast before they could spread it around and vibrate it and get it good. So they switched to a different mix. They had smaller aggregate and rounder aggregate. Perfectly fine mix. The inspector realized that mix wasn't approved for the nuclear island. It was approved for everything else, but it wasn't approved for the nuclear island. So the contractor, shame on him, he picked a different mix to help out his workers to be able to do this in hot weather. 5 or 6 structural engineers came and looked at the properties of the mix and said, it's fine. Don't worry about it. Shame on you. You shouldn't have used a mix that wasn't approved, but this one's just as good. Leave it in there. The inspector said, not on my watch, not in a nuclear structure. Take it all out. And they did. They jackhammered the whole thing out and recast it. They didn't need to, but that's the mindset. It's a nuclear structure. It's different. You have to, so I think had there been the structural engineer, had he been on the site and had they been standing next to the contractor and the contractor said, I want to use this other mix, the structural engineer would have said, okay, it's not approved for this, but looking at all its properties, I approve it. Here, go ahead, use it. We were going to get a better product because it's not setting up so fast and you can vibrate it and get higher quality concrete in the end.
That was not a US application.
I was trying to keep it secret.
Well, it means it wasn't a US inspector. That's where I'm going. So that's an important piece of information. Back to Prasad's point about margin. I look at margin as dollars. Someone's paying for the margin. If you don't need it, don't provide it. And at the end of the day, the customer pays. And you're not doing your job if you're delivering a structure that doesn't hit the performance goals as close as you can possibly get it. So margin maps the dollars, and margin could be different limit state. You could target limit state B and end up with limit state C. Someone pays for that. You target a frequency for a given limit state and you can deliver something that can achieve a much lower frequency. Someone pays for that. You don't have to. Risk-informed performance-based design allows you to target performance with a specified mean annual frequency of exceedance. We can do it. I don't see value personally, and we can argue about this later, of providing margin. Might make you sleep better at night for no good reason, my opinion.
Actually, I support what you said.
Good, thank you. Next.
I was just going to do a quick time check. Maybe one more question, and then we got to move on.
My assumption is that the frequency you presented here, that the best estimate. So you consider any uncertainty bands or any like using the 5th percentile instead of, best estimate for your design?
Excellent question. I'll let Andrew. The fragility curve's up on the screen, Andrew. Sorry.
So you're talking about 5th and 95th percentile on the fragilities or in the hazard, or both? In terms of hazard, if we can come up with a reasonable mean estimate, I think that's a tremendous outcome. There's a lot of work being done unpacking logic trees to develop the 5th percentile and the 95th percentile. You change the weights assigned to the different branches in the logic tree just based on the experience of those in the room, you get a completely different answer. The mean hazard is probably fairly stable. So if I'm doing a performance-based design, and we do a lot of it in the non-nuclear space, you use a mean hazard curve and you use a mean fragility function. And that gives you one estimate of the risk, a reasonable estimate of the risk, your best estimate of the risk, not something that's conservatively biased, unconservatively biased.
I would just add, Andrew, that I would just add,
to that answer, Andrew, that if you're using NAI 1804, you're going to do your work on best estimate, but you're going to be required to consider 5th and 95th percentiles uncertainty on both the hazard and the release.
And in terms of the structure, the fragility curve in the bottom right, the slope of that curve is related to the uncertainty. So we design structures for that entire, we integrate over the entire curve. So we consider structures at 5%, at 95%. It all goes into the rate equation. In the old days, deterministic or prescriptive, you would say, you know, a safety factor is based on the 95th percentile or the 5th percentile. So, you know, whether you're doing loads or capacities, but this considers the full range. Top right?
Top right.
Top right, yeah. So you're right. Yes. So Han was asking about the curve in the top right and whether we consider a single curve or a family of curves. And he's exactly right. I've only drawn one there, but there will be a family of curves for different intensity measures. So the intensity might be measured as an acceleration in G, but you'll have it for structures that have different periods, natural periods. So there'll be a family and there'll be a PGA. There can be other things. Yeah.
So let's be clear. So we can generate for one structural period a family of these hazard curves. So you go from the 95th to the 50th to the mean to the 95th percentile. So you can develop a family of them. Shown here is intended to be a mean hazard curve. With respect to the fragility functions, we did some work about 20 years ago where we looked at families of fragilities and integrating them across different hazard curves. We showed that if you use this, what I'll call mean fragility function, which addresses epistemic uncertainty and aleatory variability, the use of a mean fragility function gives you a really good estimate of the risk. You can do it the two different ways. Using the mean fragility function, recovered the results of the more detailed analysis, let me say. But to John's point, if I go back to the figure from NEI 1804, you do compute a best estimate, and the current practice is that you look at 5th to 95th. Whether that's right or wrong, I think that's a discussion to have going forward.
And there's a family of fragilities too. We're just showing one of them, but for any given design, we could draw all 4 fragility curves related to each of the 4 limit states.
Now, George, I think our time's up.
Yep. Yes. Hey, you gotta have somebody calling the shots here. So yes, thank you so much. That was, again, hate to cut off conversation. That's the whole point of this. Really appreciate it, but we got to move on to the next topic. We're going back to the roadmap.
Yeah, you hate to get off a subject as interesting as this, but you know, there's going to be an awful lot of discussions that are continue on this anyway, and we need to, from different perspectives, etc. But thanks again, Brian and Andrew, for that very informative discussion and interaction that we had. Thank you. This is going to be very quick because the time is running short. And we've talked about this multiple times, not only in the past at our biweekly meetings of ARCSC, but even today in various aspects. So, but I do want to point out a few things on here. And the reason is because it's something that we need to address moving forward. The 4th bullet under the first set there for priority 1, secure resources, manpower, and funding. And this is something that the implementation board is looking for from ARCSC on how do we see this moving forward in 2026. This is a priority, and I know I can continue to ask for input and feedback on people's perspective on this, and I am looking for everybody's input and perspectives on where do we see this moving forward for accelerating the timelines to have this ready for the deployment of advanced reactors. A need date, 2025 for timeline and assigned resources. And I've got that pushed out, obviously, to 2026 now. John, if you can move that up a little bit to the next paragraph, that would be great. That's good right there. The last sentence on that first one, under progress, for the first one, ARCSC is in the process of listing those standards in need of the highest priority for both manpower and funding. And that is true, and we have done that. We've submitted the priorities to the regulators, to DOE. And what I want to mention here, though, is that in conversations recently with DOE at the ANS Winter Conference that we just had in Washington with Garrett Smith, he says, if you submit a proposal for a specific need for a standard or standards with the reasoning behind it, they will support whatever effort they can. They don't want a big, I got you for so many things that need to be done, but submit specifically what you're looking for and the timelines behind it, and they will support that and act upon that. So keep that in mind. We will keep that in mind. Moving now to priority under the RIPB. Just a couple emphasis here. Update and develop codes and standards to support the RIPB approaches, and update existing codes and standards to incorporate the benefits of RIPB approaches. A lot of that's going on today in different ways, in different discussions, in different manners, and in different aspects. I mean, we just talked about structures. We've been talking about RIPB needs across SSCs, a lot of different ways in documentation and approaches, et cetera, like that. So they're all very important and they're needed. The need date of 2025, it's going to be an ongoing issue, but we need to keep addressing it and keep acting upon it as we're doing right now. I don't have anything else to add to this particular action we have. It's a continuation from 2023, and we will need to update and inform the implementation board people anything that we see that we need to modify or enhance or change, if you will, to this particular action item we have. Any comments on CS2? Okay. Thank you. That was easy. Now, this is going to be tough. AI, artificial intelligence. I'm just going to say a few opening remarks here. I'm not the presenters. We have Todd Anselmi from Idaho, and we have Jim Slider from NEI. They will provide the bulk of the discussion on this and interact with us as far as what this means, if you will, from a perspective on our involvement. I was listening on YouTube last night, very late, a discussion on artificial intelligence that was put together by IBM. I found it quite intriguing. So instead of going to sleep, believe it or not, I stayed awake to listen to it. But I think we may or may not know that AI goes back to the early 1950s. We're talking over 70 years where AI in some form, has actually been used or has been developed and enhanced as years went on. So I just want to make some opening remarks that I gathered and share them with you. Artificial intelligence is a field of computer science focused on building machines. Can't read with my glasses on. Building machines that perform tasks typically that requires humans' intelligence, that includes learning, reasoning, and problem solving. It uses techniques to process data and make decisions using everyday applications. And I think we know that. We're talking way beyond nuclear right now. It's across everything. But AI has its limits, and we need to recognize that. But it also has its benefits also, and we need to recognize them. So applications such as automation and efficiency and improved decision-making are all part of this. But there are risks also that we need to be aware of. Two of them that at least was discussed on this particular video: ethical concerns. And what does that mean? That means privacy issues when you talk about health. Safety. Well, we have safety okay involved in our nuclear applications. And human automation, if you will. And then there's a need for governance. And that's crucial, so it is used safely and responsibly. So summarizing, I want to say and leave you with AI in nuclear energy is to improve safety, efficiency, and maintenance through predictive techniques, real-time monitoring, and optimizing operations. AI is accelerating development of new reactor designs and supporting worker safety, along with accelerating research in the next generation of reactors. And that's what we're talking about. That's what we're looking at right now. So with that, over remarks, I want to turn this over to Jim Slider for his presentation from NEI on what they're doing on AI initiatives. There you are, Jim. Thanks, Todd.
I really appreciated the invitation, and Don, that was a very appropriate intro. We've all been inundated with the words artificial intelligence over the last year in particular, but a couple of years, and it's all the rage, so to speak, across our industry. And I just want to talk with you. Don had asked for a briefing on a particular project that NEI is involved in, along with EPRI and INPO, to give you a sense of what the potential for the access to the products that your standards development organizations are providing, what that could mean to the industry. So for those of you who don't know me, I work in NEI's Regulatory Affairs Department, and for the past 4 years, I've led our work on addressing regulatory impediments to innovation. And one of our top priorities over that period of time has been artificial intelligence, anticipating that the NRC would be developing regulations to assure the safe use of artificial intelligence for such things as potentially one day autonomous operation of small reactors. So for the last year in particular, NEI has been involved in this project that I'll talk to you about here momentarily. It's today recently been branded the Nuclear Industry Virtual Assistant. This was started about a year ago by the leadership of INPO, EPRI, and NEI, recognizing that artificial intelligence offers the possibility of making it easier for industry to access the trove of records that INPO has, EPRI has, and NEI has in one fell swoop. So rather than you having to go to the EPRI website, log in and get whatever you want, then go to the INPO website and do the same thing, and then NEI's website, that with a properly trained large language model and what we call federated access. You could use your credentials at, say, INPO to log in once and then access records and reports and so forth at these three institutions, providing the same sort of easy access that some of you may already have experienced in using ChatGPT, for example. So with that, if we go to the next slide. So let me just step over here. The vision of the leadership of INPO, EPRI, and NEI was to establish a platform for this federated access. Federated means you log in once, and then the software behind the scenes verifies that you've got credentials that qualify you for access to the EPRI reports and the NEI reports and so forth. It was specifically to accomplish that in a way that protects the integrity of the intellectual property that EPRI has in their trove of records and reports, as well as what NEI has in our technical reports and access to the IRIS database at INPO, so forth. But the emphasis here was to bring the three institutions together in a highly collaborative framework using artificial intelligence. Next slide, please. There are three initial use cases for this collaborative platform. One is our knowledge assistant, we call it. It's about, it envisions the user as someone new to nuclear who wants to learn about a subject, and I'll show you an example of that kind of output here in a moment, but potentially someone new to nuclear, and the emphasis of that is on accessing the trove of information that NEI has, but not exclusively what we have. It also brings in relevant information from EPRI and INPO as well. So Knowledge Assistant, here it's tagged as knowledge transfer. Also an operating experience search tool. This is to facilitate access to the IRIS database and other records in the INPO system. And then a troubleshooting tool that is focused primarily on what EPRI brings to the table with their troubleshooting database. Next slide, please. This is a key chart I wanted to walk you through. We have, let me just step over here. This is a schematic of accessing INPO's records, EPRI's records, and NEI's records into a large language model that has been developed by Atomic Canyon. They're the contractor of choice here. And we've also been dealing with NRC's Office of the Chief Information Officer to gain access to curated subsets of what's in the ADAMS database. ADAMS, one of my colleagues likes to call it effectively a landfill, because NRC for its 50 years of life has been dumping records into ADAMS. These curated data sets that we've asked for are those ADAMS records, but with more refined metadata so that you can do an intelligent search using a large language model to get more meaningful, more accurate results. So we're working right now, we've got new regs and regulatory guides in these highly curated data sets. We're going to be, NRC is going to be adding more of the generic regulatory documents to that. And so we'll, over time, we'll have that, more of that, plus an ongoing live connection to INPO, EPRI, and NEI. So the idea here is your utility staff will have a user interface that allows them through a chatbot type of interface, like you may have seen on ChatGPT, to query all of this information and pull it into their system. ideally, their company platform will allow them to integrate these results with plant-specific records, plant-specific data. So in one connection, they'll be able to draw from both the internal records and INPO, EPRI, and NEI records to get an intelligent solution. Next slide, please. The only thing I wanted to highlight here for you is right now we're in early stage testing of this knowledge assistant tool. By the end of December, the project team expects to have the operating experience tool ready for testing. That'll be drawing from Iris, as I mentioned a moment ago. And then probably first quarter next year, we expect to have the connection to the EPRI troubleshooting records ready to go. So, this is all considered to be a pilot project or trying to figure out, trying to establish the IT plumbing to make all the institutions talk to one another seamlessly, but also to get some sense of what the use will be and therefore what the cost of maintaining this system will be. So I expect in maybe the second half of 2026, we'll begin to have conversations about whether the results of the pilot and then going to a production level platform that would be durable. Next slide, please. Just want to emphasize one thing here. The parties initially involved in this project were INPO, EPRI, and NEI, as I mentioned, but also Constellation provided some initial seed funding. And along the way, several utilities have expressed interest in being part of the pilot testing phase, and that includes PG&E, Southern, OPG for our Canadian friends, and NextEra. And then as we get through the pilot testing, then we'll expand beyond that to broad use across the industry. Next slide, please. Yeah, you can see what the vision here is a scalable solution, ethical, responsible, transparent, and trustworthy, as Don mentioned from his YouTube video. Hoping to build more use cases beyond those three initial ones. And God willing, this AI platform will become something that we will all find indispensable. Next slide, please. So those of you in the back room can't read this, but maybe on your computer screens you can. It's a chatbot kind of interface like you might have seen on ChatGPT. You type in your query here. The query says, tell me about the history and purpose of Flex, identify the key references and recommend a study guide. And what the system gave back is a nice one paragraph overview of Flex, some context information, and then detailed information which rolls off the bottom of the screen here. So it's the same sort of narrative response that you get from ChatGPT and other large language models, chatbot interface that are commercially available. Next slide, please. And so if you have any questions, Rob Austin is the lead for EPRI, Ramon Martinez for INPO, myself and Kelly Volsing, who many of you may know from her time at EPRI. We're the co-leads here on this project for NEI. So that project is what we're up to for the industry's benefit. And I could, if you could go back to the architecture slide, this one here. What I would love to see, because I hear from members of my innovation task force, some frustration that the intellectual property protections on codes and standards don't allow intake into a large language model like this. They would love to be able to access ASME code, the IEEE code, and so forth in this way. And if that was, say, a fourth input to this system and protected the same way that we're protecting INPO's IP, EPRIs, and NEIs, that would be a great enhancement to the value of this system, in my opinion. Any questions for me? Ms. Franovich?
Jim, great presentation. And two things. One, why is, or where is it written that there is a prohibition against using purchased versions of the code for AI use? That's one question. The other is, has your team engaged at all with INL and some of the work that they're doing, perhaps not using AI as a platform, but automation of licensing material formulation for from design concept to submission of documents? Thank you.
Yeah, on the second question about our engagement with INL, I know that Atomic Canyon has been in conversation with INL. I don't know the details on those conversations, and I'm engaged with INL on through the Light Water Reactor Sustainability Program. So I know that much about it, but I don't know more, right to your point. And your first question was, access to the contents of standards. I don't know what those protections are. They've been reported to me by our members, but I don't, others of you here who are expert in the various codes can probably answer that question better than I.
I've heard the same thing, and I'm just trying to find where it's written. And I understand that there has to be express permission to actually upload code, even for like a company like Deep Vision, we're AI native. We use AI all the time in our day-to-day operations to be more efficient. But if we can't upload the code that we've purchased into our protected system, we have our own company version of ChatGPT, then it seems to me that that's a disservice to our ability to actually apply the code in a way that informs our design smartly. So if you ever hear where it's written, I'd be interested in knowing. Thank you, Jim.
Thanks, Rodney. Prasad, Todd, you want to come on up? Go ahead.
My question has to do with the kind of information that's available from SDOs that may not be under copyright protection, which may be one of the factors that, that's a hurdle with regard to public access. Even if it is protected, there may be some hesitation in giving up copyright protections. But ANS, for example, has a large volume of information related to the community of practice. This is for the last 5 years. We've been having monthly presentations by people who are actually practicing risk-informed and performance-based approaches, concepts, and methods. And this is public information. But what I have found, at least just in my using some AI tools, is that it's not discoverable by some of these platforms. What is it that your program can do to work with, let's say, ANS and make sure that this information is discoverable, because it's freely available for use by, all these institutions that you're talking about?
Yeah, it's a very good point. I appreciate you mentioning that. I will have to talk to my colleagues and the development team at Atomic Canyon about that.
So just wanted to, there's an online question kind of tied together. The first part is the effort in effect, quote unquote, super document control. I think the real question is how will this relate, for example, to reactor design? So you kind of have showing maybe operating plants, but does this feed into new plant design?
It potentially could in that it can draw from, if you have a question about new plant design and put it into the chat interface, it will draw from all of the NEI reports that are in the database or in the records in the system, as well as EPRI records. So to that extent, I know it will address questions about new reactors, but it's a very keen observation that the initial thinking is focused on such things as operating experience, research, and troubleshooting, which are clearly operating plant issues.
All standards are, copyrighted, and you can only get a single copies, and it's not for multiple use. So that's the reason you cannot load it into a database. And even when we procure standards, it's only for single use. Otherwise, you need to get multiple use license. I think that's what preventing it from putting it on the general use.
Thank you for that. This is Ronnie Franovich again. So does that mean that a company can't purchase it? It's an individual at the company that purchases it?
Yes.
There's something perversely wrong with that, in my view, because it seems like it's an incentivized monetary system that is the point of perverse where this is concerned, perverse incentives. Imagine that. But that's just my opinion. Thank you.
No problem. One other related question, when you integrate utilities, for example, and they have IP on the reactor design from their third-party suppliers, how are you going to protect that?
That falls in the scope of the controls that each of these companies has internally. It's not part, their information is under their protection. This model is looking back at what the three institutions have, and then it's up to the user on the utility side or other member company side, what they do with the results of that query of the institutional records. Yeah.
A quick question, last one online is the other part of using AI is how do you verify the output? How do you verify what this large language model produces?
That is the question, isn't it? And it's the paradox that we have to have enough expertise in the user to validate that the answers provided by the machinery are meaningful, credible, accurate, truthful. So you can think of this as an intelligent intern who you ask to go off and search for records and bring you back a stack of records this high, but it's up to you, the expert, to know which of those are really relevant and relevant to your question. And the same is true here.
Jim, if I could just comment that when I use ChatGPT, what I find really helpful is it'll identify the sources of the information that it scrapes from the universe. And then I can go and review it to confirm that what it's telling me is consistent and, precise contextually. So that is one of the advantages of AI that I really appreciate. And the expertise. Yeah. but expertise is needed to verify some of the more nuanced things. I agree.
So Ralph Hill, you've got your hand up. Let's see if the audio still works, Ralph. Go ahead.
Thank you.
Yeah,
I
we
was
can
just going to comment relative to how do you know that you can trust the information? And from a design standpoint, it's important to have integrated project teams. One individual can't necessarily verify some source of information and how that information may or may not affect the design of the project, et cetera. So integrated project teams are key to that, to ensure that the data used is valid.
Thank you, Ralph. That's a very good comment, and I'll just harken back. This platform really is about facilitating access to information. It's not taking the place of the integrated team or any other expertise. It's recognizing in our paper burdened industry, finding records is the greatest challenge our engineers and other key personnel face. And this is designed to help them.
And if you can still hear me, it also ties into the earlier presentation we had relative to peer reviews. So that's also key.
Thank you. Yeah. Am I on? Can you hear me? Yeah. Yeah, I just want to make a comment that you have your task group that's developing this model. And I've read in a number of sources that you need to have an independent review committee that is experienced or experts in this area separate from the developers to do an actual review to see if it's kosher, if it's consistent, there's nothing wrong, if you will. And therefore, okay, that becomes part of your verification and validation process. But that's something to keep in mind. I'm not sure the people that's part of your task group has thought about that far forward, because I know you're in the process of developing it. Just to comment back to you, Jim.
Don, thanks. That's a very good question. And part of the answer at this stage in development is the governance structure. And there is a steering committee comprised of senior executives from the institutions that are meeting monthly to review the project and ask those challenging questions as well. And the development team includes a swath of INPO, EPRI, and NEI folks as well. Yeah.
Okay, next. All right, well, I'm Todd Anselmi. Some of you online probably wondered, why is Anselmi talking about AI? So there's a lot of things I know a little bit about, and I can't even take advantage of Ronnie's comment earlier that I've slipped at a Holiday Inn. But I volunteered to facilitate this because I think it's an important subject. And when the first slide comes up, you'll see at the beginning, should the industry develop codes and standards on the approach and control? So I want to get to that question afterwards. So I'm not here, I'm going to present a little more information, but I'm not here to present to you. I'm here to facilitate conversation on what the industry and the SDOs should consider or get out of the whole AI business altogether. So I thought I'd at least start to present that. I also show here I'm the vice chair of ANS Standards Board, and I'm from Idaho National Laboratory. You can see neither of these have INL or ANS because I kind of mixed it all together. It's a hodgepodge of stuff. Next slide, John. So, and you'll see I don't have a lot of images because I've got a couple of things I'll show you in a little bit. But here, I just wanted to tell you, ANS, we had a task group got together and did an assessment of, well, what kind of things should or could be considered from an AI perspective. And it's not from the software side and development. It's just like the subject that we talked about with a question on, well, what's the validity of the information that we're using? So we could look at things like inputs and outputs. And we have a PIN that's, PIN is a project initiation notification where we're going to start working on one standard. I don't want to call it to get our feet wet, but there was some hesitancy on, well, what can we do if we do too much all at once, or should we take a first step? And one of the things that we're going to be looking at is computer vision, artificial intelligence technology. So really looking at how can we take data coming in, monitoring instrumentation out in the field and use an AI application to confirm that validity of the data, confirm that the modelings or a standard put in place to make sure that we're modeling in a standard, minimum standard condition, things like that. But some of the other things that we came up with was like operating efficiencies, process for efficient human AI integration, design and engineering requirements for digital twin integration with AI, kind of a standard for what would industry folks do when they did some integration between an AI model and the plant data. Also, even something simple as, not simple, something as standard as AI definitions, terminology, and metrics. So those are some of the things that the white paper and the assessment team came up with. And we chose to look at the one that I just mentioned, the computer vision, right? Computer vision AI. Next slide, please. The other thing I want to talk to you about is, you all heard about the Genesis mission, just came out a while ago, right? This comes from a presentation. So I've got 4 slides that I'll talk about what we're calling the Prometheus project. But as part of the Genesis mission, we're going to use AI modeling consortium led by ANL to start setting up a model, the cloud establishment through ORNL and the modeling teams. And I'll get into that next slide. So there was actually some funding that was redirected for FY27 to help support this. And they're going to use some seed model teams. Don't ask me what the seed model teams are specifically, but you'll see the objectives in 2 slides later. And we are looking for, we being the lab consortium that's working on this, they are looking for AR vendors, designers that might want to participate in this as well. So I was told to put a plug in. This just became, the Prometheus project just got advertised or just became public a couple of days ago. So there you can see that the fission energy use of AI under Prometheus has those 4 primary labs. Next slide. The first statement's kind of part of the vision, or excuse me, the mission. One little thing to keep in mind is kind of along the mission of Genesis mission is it's more than innovation. It's a national imperative to secure energy independence and outpace our global competitors. I think some of what you heard is that, and what you probably all know is we're talking, what is it, 500 terawatt hours of electricity in the next 5 years. We need internationally 179, I think, are some of the numbers for the US, right? Which we've also heard the 400 gigawatts electric by 2050. So that the whole basis for the Genesis mission too is same thing. We're going to power the need for AI, and we need the power for those conditions. So let's talk about AI. Next slide. Software platform ecosystem capable of accelerating deployment of nuclear fission power plants using autonomous design. So they're actually going to look at how can we design a nuclear facility. Okay, I don't have any details on that, and it's all just kind of new. Same thing with autonomous operations. It's not to say that this will be autonomous, from the get-go, but that's what the end goal is to look at, and then physically demonstrating it. Okay, next slide. So what would an AI discussion be without trying to apply AI in preparation for the discussion? So here I kind of asked the question, how is AI being used in the nuclear industry? Now, at Idaho National Lab, we have our own Microsoft Copilot. So we have the ability to look solely on INL licensed type stuff versus public, okay? So in our Copilot, you hit the work button and you type in your question. And I didn't go, we're going through major training. I can't remember who talked about it before, but, and it might even been during a lunch thing that Mark and I were talking about. But we are pushing very hard to utilize AI as a tool at the Idaho National Lab. So what the work button allows us to do is it looks at everything generated internal to INL, not outside. What it also does when you put in your own term, what if I were to do this or whatever, it actually looks at all of my emails. Or if I want to look at somebody else, or even ask, how would my boss write this term? It'll look at that person's emails, everything. So it goes in a matter of seconds and generates an answer. So one time I put a question in that said, what would I do? And it says, did you know you presented on this 5 years ago and you said, okay, in a presentation. So the reason why I bring that up is because this underlies one of the things that I think AI, and we brought it up earlier, AI, how can we control and manage the use of AI in a nuclear application? Where do you provide the bounds or putting the bumpers in the bowling alley to help guide AI in the right direction? That might be something we can do from a standard standpoint. But this is the answers that came up. It even talked about, one I didn't put in there, talked about an advanced reactor working group from ANS because it looked at stuff that I had done and something that my colleagues had done. So there was just some of the answer. Next slide. I can't remember. Oh, this is just a continuation. Okay, it even said, well, at INL, this is what we're using it, sensor data and equipment monitoring, which actually the person that's leading the effort at ANS is from INL. And so that's one of the things that we're looking at doing. Then cybersecurity, grid resilience, and even we've done a lot of work on batteries at INL. So it came up with that one. Next slide, please. So I asked, well, if I were to talk about AI in the nuclear industry or codes and standards, what would you suggest? And this is what it said. To spark engagement, these are the things that it would suggest that I talk to you about. The second item is kind of something that we just recently talked about. And even the last bullet about rigorous standards and oversight. So with that said, next slide, please. Oh, sorry, I have two more items. This just came from the question of how will the use of codes and standards benefit deployment of new reactor technologies? That was one of the questions I asked. And I wasn't planning to talk about it. It'll be in the slide pack. One more slide and then the last one. Even brought up risk-informed performance-based. So should the industry develop codes and standards on the approach and controls for AI? And if so, who and what? Because we are a collaborative effort amongst the standards design organizations. I talked to you a little bit about what ANS is doing. I know 4 or 5 other organizations are looking at putting a standard of some sort in place. So I thought I'd pose that question here because it could become the next phase of things that we can collaborate on. And it also allows, from a collaborative standpoint, allows us to hold each other accountable for trying to get something out if we think it's a high priority standard. So I'm gonna open the floor.
All right, I'm gonna just quickly start online. So the statement online was the last part of the presentation does not seem to comport with what we heard from NEI and on that initiative. So I've kind of interpreted this question to mean, how is the Prometheus initiative aligned or not aligned with the NEI, EPRI, IMPO effort? Or is that something to do in the future, or is that not a consideration?
I don't have a direct answer for that, positive or negative, but what I can tell you is Jim did bring up Atomic Canyon. I believe they are also involved with this project because I know they're involved with several of the INL projects. But it is a DOE independent project and it's just gotten started. So I won't say that it's not already aligned, but I'm pretty certain that there will be alignment with it. That's it. Any more?
Go ahead, Ronnie, and then we'll go to Ralph online.
Thank you. I was just going to say, should the industry, which industry are we talking about?
Yeah, because it could, I mean.
Can you repeat the question for the room?
Oh, yeah, the question was, is when I say industry, that's just a term I've been using generically, but industry, I'm referring to nuclear, but it doesn't have to be nuclear. In fact, with one of the ASME codes that I'm on for ASME Section 11 Division 2, I say Kimberly-Clark paper towel factory could utilize that code for aging management and condition monitoring. Same thing can apply here. Anything that we would apply in the nuclear industry, whether it's a nuclear application or not, it's probably how I would define it.
I would venture to guess that there is already underway work to do this by people who are in that industry, meaning, the development of computer technology for these kinds of applications, AI, automation, other things of that nature. Perhaps the question should be, who is developing codes and standards for the use of AI? Because I'm not sure that nuclear is so special that it would have anything different. Just a thought.
Correct. So Don Spellman just made a comment that just says, how is AI being used currently in nuclear? I don't think the question was, or your statement of it's already being used, you were intending that it was just nuclear. You were saying it's already being used somewhere in an application that we could relate to and actually maybe invoke similar.
Well, so maybe I'm misunderstanding the slide. Should the industry develop codes and standards on the approach and controls for AI? I interpreted that as the nuclear industry. And what I'm suggesting is this is probably not the role of the nuclear industry. Somebody's already doing it. And the question should be, who's doing it? Because we should apply the same codes and standards. Simply because nuclear is not special. It's like any other industry with its own unique hazards. So why would we go off on a tangent and develop these things for our industry when probably much more knowledgeable practitioners may already be doing it?
Correct. I don't know if I need to repeat all of that, but so I use the term industry. And Ronnie had asked about, well, the interpretation of the use of nuclear industry. Maybe I'm really referring, because again, this is just to engage a conversation, referring to us as the standards design organizations, because we do represent a lot of non-nuclear stuff. Some of us do. American Nuclear Society, obviously we represent American Nuclear Society or the nuclear industry. But what I'm really trying to engage is, do we think, we being the folks that participate in this collaborative effort, especially from the SDOs, is there a role for SDOs to develop a code and standard to assist the nuclear industry in deploying advanced reactors?
So can you hear me? I'd like to contribute.
Yeah, go ahead, Ralph.
So in the bullets, I posted some bullets up on the chat. And the first of those talks about ASME creating help contain and use of AI by developing technical safety and conformity assessment programs as a means of assuring technical standards are met. And keep in mind that Ronnie, that ASME is not only nuclear, it's also non-nuclear. They have a number of standards used widely in many different industries for V&V, verification validation, and many other similar areas. They would be one SDO that could take on the mantle or challenge, if you would. I think there's a specific need for at least industry type specific guidance, regardless of what else is being developed out there. And regarding the conformity assessment, we all know the quality of components we get. Let's just say there's counterfeit goods out there. There's manufacturers that don't do a good job in meeting the specifications. ASME has conformity assessment programs that some people love, some people don't love so much. But what they do is they do audit and survey manufacturers to ensure that they maintain certain quality levels. In this case, that they meet the requirements of the Section 3 code or the Section 8 code. So I think those types of things are what we can do. And they're not just nuclear specific. I agree with you 100% on that. So ASME could develop something that was not nuclear specific, would apply across all those different I'll say component development organizations or manufacturing organizations.
So can I just want to kind of summarize some of the online comments so we don't lose them, because there's a similar vein. I think that people are, so Larissa provided again in the chat, and the chat will be preserved just for everyone's knowledge. So she provided a link to IEC with the comment that there are already many standards developed and in development within the international community via the IEC. And which is, again, leads to the international harmonization already being there. And some have been adopted in Canada directly. Also that for reactor control applications for AI, there was a suggestion made that, hey, look at aerospace, because for those of us who flew here, you may have already experienced the landing, or at least some aspect under the control or assistance of computers and automated systems. And then from Kent Welder, again, there are already numerous codes and standards for AI, and AI is already deployed in the nuclear industry. So I think I captured as, we'll go over these. I think one action would be to kind of, again, go out and take a look at who is already developing codes and standards for AI. We've got some answers already. And also, where is AI maybe already being used in the nuclear industry? And answer the question, is there really a nuclear problem? Or is this something that, like you were saying, was broader and we just adopt a generic non-nuclear or commercial, I guess is what we call it, standard? I'm actually seeing indications that there might be some strains that relate to nuclear, but a lot of this will be just broadly developed more in the IEC, IEEE, that kind of space.
So let me get a clarifying question to Larissa. So when you say that CSA or Ken has already adopted, the IEC I thought was mostly on the modeling programming side of the tools and not on the, well, how do I as a user or user to develop a nuclear technology of some sort, I'm still going to say nuclear technology, how do I use the standard to ensure consistency in modeling, to ensure that what I'm putting in and getting out are what I need as the user, and gives me assurance, especially if it's applied to a safety related or risk important aspect. I don't know that we have any of that out there.
I have not read all of the IEC standards myself, but I know there is 42,000, I think it's 42,001, which is like an AI management system standard. So it's very high level and it's meant to apply to development and application of AI. There's also a series of like data management standards. So there's a portfolio of them. I don't know all the ins and outs of what everything covers, but again, those have been, many of those, I'm not sure if all, but many of those have been adopted by CSA as Canadian standards. Again, not in a sector specific context, but those are being considered by a number of sectors for application. I had conversations earlier this week with our oil and gas folks about whether there's a need for something sector specific there. So very relevant conversations that are happening across the board.
And just kind of continuing on the online, that Kent Welder calls out for SIL, for SIL, for software, there is no guidance yet for nuclear industry applications to his knowledge. And then, so I mean, there's a lot. We're going to capture the chat. I think as feedback, this will be something that, Todd, you and INL can take back from the discussion here.
Yeah, because the goal was, well, it could be an easy goal. It says, no, there's enough out there, SDOs stay out of it. I don't think that's the case. The hard part will be is, well, what is out there that we can utilize and what's the gap for what we think we need versus what's available, even if it's non-nuclear application.
Yeah, again, I think that's captured in the action I suggested. So
I'll go ahead, John. Yep. We're at the end of our time.
So I realize this would require a change in the position of a lot of the SDOs, but we talked about harmonization across the globe earlier. Like AI seems like a very, very good tool for that, being able to compare, here is the standard in the US, here is the standard in Japan, here is the standard, the IEA standard, here's a Canadian standard, and say, what are the actual differences, right? I would encourage the SDOs to consider that, but right now that is against all of their policies, right? My question to you, I know INL has a project ongoing to compare the DOE licensing framework to the NRC licensing framework, and I had heard AI was being utilized for that. Do you have any more information on that specific project?
I don't know if Jason Christensen is on, if he has an answer to that, but I just knew of the project. I just don't know the details on how on its approach. Oh, that's a Ralph Hill call.
This is Jason. I'm on. Can you hear me?
Yep. And did you hear the question?
John, John, can you repeat it one time for me?
Yeah, the question is, how have you been using AI and the project to compare DOE licensing requirements with NRC licensing requirements, and have you hit a wall when it comes to the standards that those two frameworks require you to use?
Yeah, I think at this point, we're ongoing and we're comparing DOE and NRC regulations and licensing pathways, but I'm not sure that we're quite deep enough in the process for codes and standards activities in there. But it will eventually become an item that has to come up, and so I'd actually look forward to talking more with you about this and anyone else that would like to, because I think it's something we have to focus on going forward.
Yeah, again, and just making sure you get the feedback you're looking for. You're getting a lot of it in the chat again online. So I'll point out, so again, it was pointed out that the IEA just sent around an AI use a questionnaire for the nuclear industry that's kind of similar. So that's obviously something that's in parallel. And then again, Larissa pointed out that the US, UK, and Canada, the regulators issued an AI principles paper last year. So again, I think there's a lot of good tidbits here in the chat. And again, we will be capturing that and sharing that. So
great. Yeah. But the comment was that IEEE has several AI standards as well. I'm not familiar with them. I thought they were also geared, in the IEEE world. So, and the IEC was looking at it from a software and programming standpoint. All right, I'll turn it over back to Don for wrap up.
Sure. Yeah. All right, thanks, Todd. Thanks, Jim. This is a subject area that I see it's never going to be stopped. It's across the whole industry from A to Z, with nuclear only being in the N category of the alphabet. And as I think as Andrew was pointing out, there's an awful lot of interaction we got and comments back on AI. We do have a recording, okay, of this particular workshop. So we're going to pull up an awful lot of information that may be buried someplace to pull something together, okay, that we can collaborate and pull some of the action items and suggestions on ways to move forward on AI anyway. That'll probably, without a doubt, be provided as part of a bi-weekly meeting, okay, as part of ARCSC. And we can always expand that out as needed and necessary to participants that are part of the workshop. So, yeah, Andrew, go ahead.
yeah, and I did capture maybe 5 action items I think that were at least pretty clear. So if you want, let me know if you want, when you want me to, if you want me to share.
Is this just on AI or anything else?
Oh, the whole meeting, yeah.
Yeah, go ahead, sure.
I assume
Yeah, go
we're
ahead.
in the wrap up and follow up actions here.
Sure, go ahead.
Okay. Yeah, so just for everyone in the room and online, here's what I captured today. The first and foremost was a good comment that really we need to flag closure or how actions related to gaps and standards have been addressed. So, I think that's something that we can certainly
That's a
do.
yeah, that's a closure item. We
Yeah,
need to do that, yes.
As a dashboard provided to everyone. So that's the first. The second one was one that, there was a question about how these codes and standards were prioritized. So I think an easy thing for us to do, we'll share the criteria for that prioritization because we've covered that in previous meetings. So we already have those materials. So we'll share those as another action. I do want to kind of point out that, Ralph Hill, you've been very active, and I think we will want to highlight PSD 1 because it does touch on a lot of topics, including RIPB. So this was started before ARCSC, but certainly I think with it being issued, it's coming out at kind of an opportune time. So I think PSD 1 from ASME is another probably an interesting design standard that's worth highlighting. The fourth is I think the question I heard was really kind of spread across a lot of topics, but how can the IP and copyright of various standards development organizations, is there a way that that can be shared so that it can be leveraged better for AI applications? Because again, we heard a lot of different ways that it could be used, and that this seems to be a common question. So I think that's just something to take back to the SDOs, and this would be a good forum to maybe to address that. And then number 5 is really what we just talked about, which is who is already developing codes and standards for AI. Is this really a new specific, is this really a topic for nuclear only? Are there aspects that maybe are nuclear specific? But first and foremost, we kind of have to understand, like you were saying, who's doing, who's already active in this area. If there's already work underway, then there's no need to repeat it. So those are the 5 I got. Yeah. Yeah.
Just ask you.
Hold on, Prasad.
The product that we produce, this guidance document that we are working on for the task group on RIPB, how will that be actually used to close out the roadmap action item?
Okay.
That's correct. That is the deliverable out of that CS2. You are correct.
Well, I think Prasad had it was a question, right?
Yeah, right. Because that's not clear from your description of all the action items. If there is a product delivered on one of those action items, how is that going to be used?
So,
okay. So again, that follows up with some of the other comments that have come out. How do we use the deliverables from CS1 and CS2 moving forward after we capture them by the process? And that will be identified also. So Andrew, we ought to document that also, yes.
no, yeah, that's number 6 is, well, number 6 is actually to address that question.
Right.
How does that align with the completion of CSO2? So, got it.
Okay.
That's all I've got.
Okay. Does anybody specifically here in the room have any notes they may have taken, okay, that can lead to a action item moving forward? Anybody online? Okay, just summarizing, I shared with John earlier that we can definitely use the recording of this workshop to gather any action item that may be part of the discussion that happened today. And on a bigger picture, I see an action item for putting together, if you will, a task group of designers. We've tried this, all right, and we need to do it moving forward on some of these things that were discussed today as part of design needs. And I don't know, how soon we can have that, but it's something okay that I think we need to address independently or collectively. So I'll talk to John about that on what the actual minutes come out of the recording today and actually see where some of the importance or significant points came out.
So, yeah, and the good news is there's also will be an AI generated transcript. And so since it's AI, it can be also searched using AI.
Correct.
So we'll have a way to query that.
Yeah, John.
I just want to second back that looking around the room, I see one developer in here, right? Like we've got one developer left in the room. We've got a bunch of code people. We've got NEI. We've got SDOs. We've got the fact that we have one developer in here in person is a major issue. We need to step up developer participation and input. And if we're not getting that in-person input in this room, like we're failing at our job as ARCSC.
Maybe an action coming out of the workshop is to reach out to developers and ask them why they did or did not participate. And if they didn't, what could be done to entice them?
And that's turning the sheet over from we need to pull it. Why haven't they been part of it? And we've tried for a couple of years.
How many are on? But it's always it's ongoing.
There's
40.
Yeah,
There's
Frankie,
41 online right now.
Who was that? Yeah, go ahead, Jason.
Yeah, there's 41 participants online right now.
Oh, that's about 2/3 have dropped off already.
Yeah.
I know, I understand that, but I was looking at the total. Okay, yeah, Frankie, go ahead.
I had one follow-up from earlier. It was actually during your presentation when you were talking about supply chain, and you said that you wanted to follow up to get more participation from supply chain and get that into the codes and standards information.
Well, yeah, we're tied into the supply chain action that came out of the recent report, and nobody's reached out to ARCSC, and I can tell you that. So how do we reach out back to supply chain and say, what do you need from us as being a player for supply chain demand and needs for the industry? So that could be an action item, yes, Andrew and John. Yeah, that's a good point. Yeah, thank you. We'll see. Other comments? Is you think as minimal they might be, not important, whatever. And I. Hey, we finished. Oh, I'm sorry.
just had
Yeah.
one
Okay,
thought.
Ralph. Yeah, I just saw your hand. Sorry, Ralph.
Yeah,
Go right
I
ahead.
just had one thought. Can you hear me? And can you hear me?
Yes. Yeah. Go ahead.
So I thought if earlier in the meeting we asked for where is some documentation of what's really been done in the last 4 years that the developers, the manufacturers, designers can actually use. And so you're looking for the supply chain. You need to feed back to them that positive, what has been accomplished, what you're doing, what this ARCSC is done that's helping them, rather than just take up time in a meeting. So
No, I hear you. Yeah, we can feed them rather than looking for them to feed us. So it works both ways, but I hear what you're saying. Appreciate that. Yeah. So we need to capture that, and I think we have already. Anybody else online comment for actions moving forward? You know, one thing that's emphasized in the roadmap report again is what do we need to do to accelerate codes and standards in needs for the designers so it meets their deployment schedule? That's what's stated. And Ronnie from Deficient provided her perspective on what they're doing and what their needs are. We never got feedback from anyone else. I'm not sure, okay, they're ready to share that with us because they're in the process of doing and planning what their schedule is moving forward. So 2026 to 2028, you know, we're talking about a time frame like that. This is near term. I consider that near term. So, and how do we pull in the NRC to support all this? It's all part of the integration efforts. So, any final comments from anyone? Yeah, Mark.
Yeah, I have just a couple comments, maybe more pieces to plug into the puzzle, but I know in past meetings we've talked about, and I'll look to you and Andrew, that during one of the RIB meetings, that there was an offer made by the RIB that, hey, identify what standards need to be developed, you know, with some specificity, and we will produce some staff to focus on, you know, provide some committed resources to get those things done. I don't know if anything came of that, or if we can produce a number of needs where we could get companies to commit to that. That was one thought. The other idea that I have, you know, the DOE money is somewhat elusive, and I think you probably got some insights at the ANS meeting last week in your conversations, but I know in the conversations I've had with Mei Lee, who heads the AMMT for DOE, you know, she was like, we would love to hear more about what you need. And
What we're doing and what they need to know.
Yeah, rather than them producing things and hoping someone can use it, they'd like to get some specificity on what they can do, because I think they really want to help. And they've already got some appropriated resources there that they're going to use on something, and they're going to test or build or research something. We might as well tell them what we need. So you know, and these ideas have been bounced around before, but I think as we try and move from the prioritized list, and we're looking for resources and means to get these things done, with just a couple things to keep in mind, that's all.
No, and I appreciate that. And summarizing for everybody, we did bounce off the implementation board members at a response back to them where they say, we can provide resources, especially from a utility perspective, if you need help, okay, on codes and standards development. So that was sent to them. We provided the priority standards from all the SDOs and reiterating that as part of the ARCSC submittal. And they said, thank you, but there was nothing specific that came back. What we got, at least from the ANS consensus committee, was who they had on the consensus committees. They had the appropriate number of utility representatives. So they were okay, at least on the ones that we had on our 8 consensus committees. We tried, we're still working with them. You know, it's something that's difficult, but they came out and they asked us, how can we help? So I think we need to revisit that, maybe characterize it in another way, where they're willing to give resources or manpower. That would be great. I think we need to recapture that again and maybe present it to them in a different way. And your point on the AMMT initiatives and stuff like that, I really think we need to be smart here and identify what standards are really important and provide that information as an example to DOE, why this is so important for this reason, and we need X number of dollars to do this. They will look at it very closely. That's what I've been told. So I think that's a follow-up that we need to look at very closely as part of our 2026 accelerated efforts, if you will. That's all I got. So without further ado, as they say, I want to thank everybody for their presentations and for everybody that participated. I thought this was a very good workshop. Thank everybody online that's still online for all your participation and listening. And we'll follow up with John, some type of information. It's probably going to be relatively lengthy on what transpired here on the workshop, but that's up to you. But I think it'll be right to the point because I know how you write and I know how you capture stuff. So look forward to you pulling something together. You have any comments you want to make, John?
No, I'll probably give a little bit of a week, maybe at least to get something out there. Probably get a little bit out more, maybe a little bit longer to get some more time. So, but we're going to be focusing to get it on the ARCSC website. Yeah. Okay. Andrew, any final comments? Okay. Well, thank you again, everyone. Safe travel home wherever you're going, and we'll be in touch. Thank you.
Thank you.